front of the stage here, since we will begin the opening ceremony in less than 15 minutes. Thank you very much.
Cek. Cek.
Selamat pagi dan selamat datang kepada Bapak Ibu, teman-teman yang sudah hadir di gedung Fakultas Kedokteran. Selamat datang. Kami infokan sekali lagi kepada Bapak Ibu untuk mengisi tempat paling depan terlebih dahulu ya Bapak Ibu. Karena mengingat ada kamera, kita akan mengadakan acara secara hybrid. Dimohon kerjasamanya untuk mengisi tempat paling depan terlebih dahulu dan sebentar lagi acara akan segera dimulai. A very good morning to all. Welcome to Faculty of Medicine Udayana University Denpasar. Now we would like to invite you all to everyone who has just arrived at Professor Jelantik theater room here in the Faculty of Medicine. We would like to invite you all to please fill the seats available at front, since we will begin the opening ceremony in a few minutes. Once again, we would like to invite everyone who has just arrived to please fill the seats available at front, since we will begin the opening ceremony in less than 15 minutes. Thank you very much.
Assalamualaikum warahmatullahi wabarakatuh. Salam Om Swastiastu, salam kebajikan dan salam sejahtera bagi kita semua. Nama saya Excelsa dan rekan saya Dayu merupakan kesempatan yang luar biasa bagi kami untuk menjadi pembawa acara di pagi yang indah ini pada tanggal 25 Oktober 2025.
A very good morning to all, to our excellencies. Ladies and gentlemen, it is our honor to welcome you all here at Prof. Jelantik Auditorium Udayana University Denpasar, Bali on Saturday, October 25th, 2025.
Yang terhormat, Rektor Universitas Udayana, Profesor I. Ketut Sudarsana, ST PhD, yang kami hormati, Presiden The Southeast Asian Mathematical Societies, Profesor Dr. Intan Muhtadi Detiana, MSI, Presiden The Indonesian Mathematical Society, Profesor Dr. Andes Davik, MSc PhD, Wakil Dekan 1 FMIPA Universitas Udayana, Dr. Insinyur Agus Sanjaya, Eskom Mkom, Ketua Panitia IICMA 2025, Profesor Dr. Sutarto MPD, keynote speakers pada conference hari ini, dan tamu undangan yang berbahagia.
We would like to have a warmest greetings to everyone and all distinguished guests, ladies and gentlemen, who has just arrived and your presence here, to His Excellency Rector of Udayana University, in this case represented by Vice Dean of Faculty of Mathematics Natural Science, Udayana University, Her Excellencies President of the Southeast Asian Mathematical Societies, the Honorable President of Indonesian Mathematical Society, or IndoMS, the Honorable Vice Dean of Faculty of Mathematics Natural Science, Udayana University, the Honorable Chairman Committee of the IICMA 2025, all the respected keynote speakers for today's conference, as well as distinguished guests, ladies and gentlemen.
Pertama-tama, mari kita mengucapkan syukur kepada Tuhan Yang Maha Esa yang telah memberikan petunjuk, kebahagiaan, kesehatan, dan rahmat-Nya, sehingga kita bisa hadir dan berpartisipasi dalam acara hari ini tanpa kendala apapun.
Once again, a good morning to all excellencies, invitees, keynote speakers, participants to the opening ceremony of International Conference on Mathematics and Application 2025. Considering many challenges the world faces today, the conference aims to discuss these topics and facilitate knowledge exchange among researchers, and additionally, this conference will be encourage global collaborations among participants. And to inform you everyone that the event will be conducted in a hybrid format, allowing for both in-person and online discussions conducted.
Agenda berikutnya adalah pertunjukan tari pembuka oleh para mahasiswi Universitas Udayana, yaitu Tari Cendrawasih. Sekilas tentang tarian ini terinspirasi dari burung surga di Indonesia. Di Bali, burung surga ini dikenal sebagai manuk dewata, burung para dewa. Tarian ini ditampilkan oleh dua wanita, satu memerankan burung jantan dan satu memerankan burung betina. Gerakan dan lincahnya burung jantan menunjukkan keindahan untuk menarik perhatian burung betina.
And to continue the opening ceremony today, allow us to steal your attention on the stage to witness the beautiful welcoming dance that will be presented by our beautiful Balinese dancers from Udayana University. And a glimpse of this wonderful dance is inspired by the bird of paradise in Indonesia, and in Bali, this bird of paradise is known as Manuk Dewata, or the bird of the gods. And the dance is performed by two women, one portraying a male bird and one portraying a female, takes the form of a mating ritual, and the attractive and agile motion of the male birds showing off the beauty to attract the female. Therefore, we present you Tari Cendrawasih, performed by two women, one portraying a male bird and one portraying a female, takes the form of a mating ritual, and the attractive agile motion of the male bird.
Selanjutnya kita akan menyanyikan lagu kebangsaan Indonesia Raya dan himne Universitas Udayana. Hadirin sekalian, untuk peserta offline dimohon berdiri.
To strengthen our nationality, we would like to invite everyone to please arise and stand up as we will be singing national anthem of Indonesia and University anthem of Udayana.
Indonesia Raya. Mohon untuk tetap berdiri karena acara selanjutnya yaitu doa. Seluruh hadirin disilakan untuk menyesuaikan sikap doa sesuai agama dan kepercayaan masing-masing.
Ladies and gentlemen, please remain arise or stand up as we will continue to our swift or quick praying session. This is our national gesture to God so that the conference will start and end very smoothly. Please adjust your position according to your religion or belief. Praying starts now.
Terima kasih, hadirin disilakan duduk kembali.
Ladies and gentlemen, please be seated.
Agenda berikutnya adalah sambutan oleh Ketua Panitia IICMA 2025, Profesor Dr. Sutarto, MPD. Kepada Prof. Sutarto, disilakan.
Come closer to the opening remarks. A report remarks from Chairman of the Committee of IICMA 2025 to the Honorable Prof. Dr. Sutarto, MPD. The stage is yours.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Om Swastiastu. Honorable Rector of Udayana University, Vice Dean of the Faculty of Mathematics and Natural Sciences, Udayana University, Professor Intan, President of SIMS, and then distinguished keynote and invited speaker, respective colleagues, organizing committee, and dear participants, good morning, ladies and gentlemen. On behalf of the organizing committee, it is both an honor and great pleasure to welcome all to IndoMS International Conference on Mathematics and Application IICMA 2025. This conference is organized by Indonesian Mathematical Society, IndoMS, in collaboration with regional IndoMS BALI-NUSRA and Udayana University. And it's being held a hybrid form in Udayana, Bali on October 25 to 26, 2025. This year, we are proud to welcome more than 250 participants, including 155 presenters from 7 countries: Indonesia, Turkey, South Korea, China, France, India, and Malaysia. Your presence here, our shared commitment and dedication of advancing mathematical sciences and their application through innovation, research, and international collaboration. Ladies and gentlemen, IICMA 25 serves as an important platform for mathematics community to discuss, exchange knowledge, and expand network of cooperation across diverse domains, including advance in mathematical optimization and application, artificial intelligence, and machine learning, as well as cryptography, graph theory, signal processing, and other related fields. On this special occasion, allow me to express my deep gratitude Professor David, PhD, President of IndoMS, for his invaluable guidance and leadership in the organization of this conference. To Professor Iketut Sudarsana, PhD, Rector of Udayana University, for his remarkable support, and to Prof. Dr. Randa Niluh, Dean of the Faculty of Mathematics and Natural Science, University of Udayana, for her collaboration and contribution to success of this event. And then I would also like to extend my sincere appreciation to all plenary speakers, paper presenters, and participants for your active engagement, valuable contribution, and then enthusiasm in making this conference a success. My highest appreciation also goes to the entire organizing committee for their hard work and dedication and commitment in ensuring that event runs smoothly and then meaningfully. May IICMA 25 be a productive forum that imparts fruitful discussion, foster meaningful collaboration, and then Once again, welcome to IICMA 2025. May this conference bring inspiration, new insight, and then valuable outcome for everyone. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh. Om Santi 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 Om.
Terima kasih kepada Prof. Sutarto atas sambutannya. Agenda berikutnya adalah sambutan oleh Presiden IndoMS, Profesor Dr. Andes Davik, MSc PhD. Kepada Profesor Davik, disilakan.
Following to the next agenda is a welcoming remark delivered by the President of IndoMS. We invite the Honorable Professor Davik, MSc PhD, to come on stage.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera, salam, Om Swastiastu, salam kebajikan, rahayu. Honorable Rector of Udayana University, Vice Dean for Academic Affairs of FMIPA UNUD, Universitas Udayana, Dr. Insinyur Ngurah Agus Sanjaya, Eskom, Mkom. The President of SIMS who already joined with us here, I really appreciate for her effort to visit me offline. Professor Intan Muhtadi Alamsyah, distinguished keynotes and invited speaker, respected colleges, organizing committees, and dear participants, and good morning, ladies and gentlemen. It is a privilege and great pleasure on behalf of the Indonesian Mathematical Society to extend a warm welcome all of you to the IndoMS International Conference on Mathematics and Application 2025. This conference is organized by IndoMS in partnership with the regional IndoMS BALI-NUSRA Udayana and Udayana University, and this conference is held in hybrid format tomorrow, 2 days, and tomorrow 25 till 26 October 2025. Please allow me also to first acknowledge our distinguished speakers who have graciously joined us to share their experience and their expertise offline or online. I would like to invite Professor V. Lokesa from India. Please say hello to participants. And also Dr. M. Venkatachalam from India, say hello participant, and our also distinguished invited speaker, Professor Dr. Komang Darmawan, PhD from Udayana, Bali, and the last from who joined offline, Professor Shafruddin Said, SSC MSc, is already here. And the other invited speaker who will join online, and they already confirmed that they can join this conference, Professor Yilmaz Simsek, Professor Dr. Ismail Nasicanggul, all of them from Turkey, and also Professor Adelmaid Biat from France. We deeply appreciate their valuable contribution, and we thank them too for investing their time and intellectual in this forum. We sincerely hope that this conference will provide a rich and rewarding experience for all participants, fostering meaningful discussion and collaboration across various fields of mathematical sciences and its application. It is our appreciation to each session, whether in the form of keynote speaker speeches, invited talk, or interactive discussion, will inspire new insight, spark innovative idea, and create opportunity for further research and application. I wish finally all of you great a success throughout this conference and beyond as we work together to further the impact of mathematics on the real world. Again, thank you. Wassalamualaikum warahmatullahi wabarakatuh. Om Santi Santi Om. Thank you very much.
Terima kasih kepada Profesor Dafiq atas sambutannya. Agenda berikutnya adalah sambutan oleh Presiden SIMS, Profesor Dr. Intan Muhtadi Detiana MSI. Kepada Profesor Intan, disilakan.
Proceeding to the next agenda is a remark from the President of the Southeast Asian Mathematical Society, the Honorable Professor Dr. Intan Muhtadi Detiana. The floor is yours.
Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Honorable the Rector of Udayana, Vice Dean of FMIPA, the President of IndoMS, the Governor of BALI-NUSRA, the plenary speakers, and respected colleagues, organizers, and participants of IICMA 2025. Good morning and warm greetings to all. It is a great pleasure and honor on behalf of the Southeast Asian Mathematical Society to extend my warmest congratulations to the Indonesian Mathematical Society, especially the BALI-NUSRA chapter, for organizing this year's IndoMS International Conference on Mathematics and its applications. This conference brings together mathematicians, educators, researchers, and students from across Indonesia, Southeast Asia, and beyond to share new insights and explore the evolving frontiers of mathematics and its many applications. In today's rapidly changing world, driven by data, technology, interconnected system, mathematics continues to play a central and unifying role. The themes feature IICMA 2025 from pure and applied mathematics to optimization, artificial intelligence, and computational science, reflect how deeply mathematics is intertwined with innovation and discovery across disciplines. As President of SIMS, I take pride in how conferences like IICMA strengthen the mathematical ecosystem of our region. They serve as bridges, connecting institutions, fostering collaboration, and nurturing the next generation of mathematicians. Through such gatherings, we build not only knowledge, but also friendship and trust among mathematical communities in Asia. I encourage all participants to make the most of this opportunity, engage actively in discussions, explore new partnerships, and consider how the insights shared here can inspire further research and education in your own institutions. On behalf of SIMS, I extend my sincere appreciation to the organizers, sponsors, plenary and invited speakers, and all contributors to their dedication and effort in making IICMA 2025 a success. May this conference be fruitful, inspiring, and memorable, an event that continues to advance mathematics in Indonesia, Southeast Asia, and the world. Thank you, and I wish you all an engaged and rewarding conference. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Prof. Please be seated.
Terima kasih banyak kepada Prof. Intan atas sambutannya. Agenda berikutnya adalah sambutan sekaligus membuka konferensi secara resmi dengan pemukulan gong oleh Wakil Dekan 1 FMIPA Universitas Udayana, Dr. Insinyur Agus Sanjaya, Skom, Mkom. Kepada Dr. Agus Sanjaya, disilakan.
At last, to officially start the opening ceremony today by delivering opening speech, followed by striking gong, marks the official opening of IndoMS International Conference on Mathematics and its Application 2025. Joining us today, we kindly invite His Excellency Vice Dean of Faculty of Mathematics and Natural Science, Udayana University, Dr. Agus Sanjaya, Skom, Mkom. The floor is yours.
Your Excellency, the Honorable President of IndoMS, Prof. Dafiq, the Honorable Governor of IndoMS BALI-NUSRA Region, Prof. Sutarto, the Honorable President of SIMS, Bu Prof. Intan, mohon maaf, distinguished plenary speakers, presenters, and participants, ladies and gentlemen, Om Swastiastu. Assalamualaikum warahmatullahi wabarakatuh. Good morning and may peace be upon us all. Praise be to God Almighty for His blessings and guidance that enable us to gather here today at Udayana University for the opening ceremony of the IndoMS International Conference on Mathematics and Applications, IICMA 2025. It is indeed a great honor and a profound privilege for me, on behalf of the Faculty of Mathematics and Natural Sciences and Udayana University, to extend my warmest welcome to all of you, distinguished scholars, researchers, and professionals who have come from various institutions and countries to participate in this significant academic occasion. This conference stands as a testament to our shared commitment to the advancements of knowledge. It provides a distinguished platform for the exchange of ideas, insights, and innovations in the field of mathematics and its diverse applications. Through this forum, we aspire to foster meaningful dialogue, promote collaboration, and inspire new discoveries that will contribute to the progress of science and to the betterment of humanity. Moreover, it is our sincere hope that this conference will strengthen our collective efforts in achieving the sustainable development goals by reinforcing the vital link between research, innovations, and community empowerment. Allow me to convey my highest appreciation to the organizing committee for their dedication, perseverance, and professionalism in preparing this event. I also extend my deepest gratitude to all supporting institutions, sponsors, and partners whose invaluable contributions have made this conference possible. Ladies and gentlemen, let us embrace this opportunity not only to share knowledge, but also to build networks, cultivate collaborations, and inspire one another for the advancement of mathematics and its application in addressing global challenges. With those remarks, and with immense pleasure, I hereby declare the IndoMS International Conference on Mathematics and Applications, IICMA 2025, officially open. May this conference be fruitful, enlightening, and inspiring for us all. Thank you. Om Santi 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 Om. Wassalamualaikum warahmatullahi wabarakatuh.
Can we have a round of applause, ladies and gentlemen? Bapak Dr. Sanjaya, kami silakan untuk tetap berdiri di atas panggung Bapak, karena agenda berikutnya adalah sesi penandatanganan MOU atau Memorandum of Signing of Understanding, dan ini akan dilanjutkan oleh Prof. David juga. Kita silakan Prof. David untuk maju ke atas panggung juga. And to Dr. Agus Sanjaya, please remain on stage as we will begin to do MOU signing session. Therefore, once again, we would like to invite Prof. David as the representative of the President of Indonesian Mathematical Society to come on stage. Silakan Bapak Prof. David dan Bapak Dr. Agus Sanjaya. Yes, we would like to invite as well a representative from India, Professor Lakesha and Prof. Sutarto, and this is the MOU signing as well. Oh, okay. Baik. Yes, we would like to once again to inform everyone that this is an MOU signing between representative of India and Udayana University. And to have this momentous moment, we would like to invite the cameraman, videographers, to capture the moment.
Ini dibaca MOU between ini dan between ini ya, ini pertama. Ya, nggak usah langsung dibaca.
And once again, ladies and gentlemen, we would like to inform everyone, and ladies and gentlemen, this is a memorandum of agreement between Department of Mathematics, Kongunadu Arts of Science College, Coimbatore, Tamil Nadu, India, and the Faculty of Mathematics and Natural Sciences, Udayana University.
Beda-beda. Yang ini memang
We invite all of the photographers to capture the wonderful moment here, and this is also a real-time moment to have a memorandum of agreement between Department of Studies and Mathematics, Vijayanagara Sri Krishna Devaraya University, and the Faculty of Mathematics and Natural Science, Udayana University. So everyone, please capture the moment if needed. And can we have a round of applause for this momentous moment? Incredible. And we would like to invite all of the, it's already documented, yeah? And okay, that's the end of the MOU.
Dimohon kepada Dr. Agus Sanjaya, Profesor David, Profesor Lokesa, Dr. Venkata Chalam, Profesor Syafruddin, Profesor Komang, Profesor Intan, dan Profesor Sutarto disilakan menuju ke atas panggung untuk pemberian cenderamata sekaligus foto bersama.
We would like to invite Dr. Agus Sanjaya back and Professor Dafiq as well as Professor Lokesha, Dr. Venkata Chalam, Professor Shafruddin, Professor Komang, Professor Intan, and Professor Sutarto to come on stage. And there will be, this is an honoring our invitees' guest presence in the momentous opening ceremony. And there will be a token of appreciation that will be delivered by Dr. Ika as Secretary of the Indonesian Mathematical Society. Therefore, we would like to invite Ibu Dr. Ika to come on stage and please give the token of appreciations. Silakan Ibu. Our videographers and photographers, please be ready. And this is the moment to be captured. And the committee, if you would like to take pictures to capture the moment, please. The camera ready. Ladies and gentlemen, huge smile. And 1, 2, 3. Okay, thumbs up. Okay, 1, 2, 3. 3, 2, 1. That's it. That's the one. Can we have a round of applause again? Thank you very much. And now, okay, there is a striking gong, yeah, for marking the official opening of the ceremony. And okay. Now this is marking the official opening of the Indonesia International Conference on Mathematics and Application 2025. A round of applause once again. One more. That's it. Thank you very much, Bapak Dr. Agus Sanjaya. And to everyone, please be seated back. Now we proceed to the next agenda. Ladies and gentlemen, everyone, please a round of applause again for the energy that concludes our opening for today. But before that, there is one thing that will be delivered once more. There is a token of appreciation from India, ladies and gentlemen. We would like to invite again back Dr. Agus Sanjaya, Vice Dean of Mathematics Natural Science Udayana University, Professor Komang Darmawan, Professor Dafiq, Professor Sutarto, please come on stage or perhaps on the floor, that's fine. There will be a token of appreciation from Professor Lokesha from University of Vijayanagara Sri Krishna Devaraya, India. We would like to invite again Professor Lokesha to deliver the token of appreciation all the way from India. amazing. Once again, a round of applause. And please, if you would like to take pictures, this is your time to shine. Big smiles. That's it. 1, 2, 3. And 3, 2, 1. Okay, thank you very much. A round of applause. Again, thank you very much, everyone, ladies and gentlemen. That's it, everyone, ladies and gentlemen. That is our opening ceremony is concluded, and we would like to thank everyone, invitees, ladies and gentlemen, para tamu undangan yang sudah hadir pada hari ini. Dan izin Bapak Ibu, sekali lagi kami ada foto bersama, group photo. Perhaps you may only stand up on your seat. Just remain on your seat and please arise. And the photographer will be captured your moment here. We would like to invite everyone to please arise. Everyone also at front as well as at the back. And this is the moment, Bapak Ibu Panitia mungkin bisa di-capture. Dari atas sini silakan. Yes. Mungkin ya, kakak-kakak silakan bisa please gathered around at the center so we could see everyone and it is fulfilled ya at the center area. Okay. Okay, on my count, 3, 2, 1. Okay, thumbs up. And perhaps say Bali, yeah, with our huge feet. On my count, 3, 2, 1. Bali. Okay, no, I cannot hear anything. Once again, 3, 2, 1. Bali. That's it. Thank you very much. Thank you. That's the energy. Please, everyone, be seated. And now, as our opening have concluded, we would like to invite everyone for a short coffee break. And kepada seluruh Bapak Ibu yang berada di dalam ruangan, and as the opening ceremony ended, we are now reaching the main agenda for today's conference. But before that, please enjoy our coffee break that is already provided outside of this room and quickly come back to your seat as we will now begin the plenary session as well. Once again, we would like to invite everyone to please enjoy our coffee break, and if you need a toilet break, this is your time to shine. And we will now begin the plenary session as well in shortly. Thank you very much.
Agenda selanjutnya adalah coffee break. Kepada seluruh peserta yang berada di ruangan atau yang hadir secara offline, disilakan menikmati coffee break yang telah disediakan tepat di luar ruangan ini dan segera kembali karena dalam waktu yang bersamaan sesi plenary akan segera dimulai. Terima kasih.
I'm very pleased to see you here and welcome all of you to the IndoMS International Conference on Mathematics and Application 2025. Before the presentation begins, let me inform you how the session will run. First, the keynote speaker will be invited for presentation on maximum 45 minutes, consisting of 30 minutes for presentation and followed by 10 minutes for question and answer session. Let us now begin with the first speaker. Our first speaker is Professor Lokesa, Professor and Chair of the Department of Studies in Mathematics, Vijayanagara Sri Krishna Devaraya University, Ballari, Karnataka, India. He brings 30 years of teaching experience, including 14 years as a professor, and has authored 239 publications in national and international journals. He has delivered 126 invited talks at conference and over 130 workshop and conference presentations. His contributions have been recognized with the RRP Karnataka State Award for research publication in 2016 until 2017 from the Department of Science and Technology and also the IOSR Research Award. His research spans chemical graph theory, functional analysis, algebraic graph theory, data science, and also machine learning. Professor Lokesa, the time is yours.
Good morning. Namaskara from our India. Honorable Rector of Udayana University, Dean of Faculty of Science and Natural Sciences, Udayana University, distinguished professors, invited speakers, organizing committee member, and dear participants. Good morning, ladies and gentlemen. First of all, I thank you for IndoMS International Conference on Mathematics and Application, IICMA 2025. Is organized by Udayana University, IndoMS collaboration with regional IndoMS BALI-NUSRA Udayana University. And it is a hybrid conference. Many of our Indian participants are in the online from October 25, 26, 2025. And my special thanks to Professor Komang. He has taken a lot of care and concern about organizing this conference. And also my friend and well-wisher of Indonesia, that is President of Indonesian Mathematical Society, Professor Dr. Dafiq, and Professor Inchan, and Professor Sudarshan, Professor Dram, and Dean of the Faculty of Sciences, Natural Sciences, those who are involved in this, organizing this conference. I am special thanks to them, and thank you very much for giving an opportunity to give this, giving an invited talk in this wonderful conference. Let us start my presentation. Good morning. Good morning. Today my talk is presenting, the title of my talk is A Study on Degree-Based Topological Indices of Graph Classes and their application to carbon nanostructures in QSCPR and QSER modeling. Actually, this joint work I done with my one of research scholar, that is Deepashri. She done many works related to the degree-based topological indices and their classes and carbon nanostructure. This talk is majorly divided. Next. Divided into 6 stages. Some of the objectives of my work and some abstract introduction and some literature review and some few definition we will discuss here, because many researchers are there, young researchers are working in this area, that's why, and some major results and discussion, and finally we will give some scope of the future work. The objective of this topological indices include extremal values of several classes of graphs, unicyclic graph, maximal, we can find the maximal and minimal degrees, class of connected graphs, and we can show some of the derivatives of carbon nanostructures are being developed with the advanced chemical, electrical and physical properties. These topological indices can be effectively utilized to sort out the stable isomers of the compounds. And also the study computing the degree base, here we are considered only for the degree based topological indices with the help of some polynomial structure, M polynomial and NM polynomial. There are 2 types of polynomials we included here with the carbon nanostructure. With the help of the physical features and chemical reactivity, biological activity in QSER and QSPR models. We are discussing some of the issues here, and statistical and regression analysis of various topological indices of different class of graphs with their correlation have been studied and analyzed in last 3 years. Next. These are the important, next slide. You know that in mathematical analysis, majorly in mathematical chemistry, the topological indices have been very valuable for predicting the properties of compound from the molecular structure. Topological indices is a numerical term popular in mathematical chemistry, and these quietly some quantities are widely used to predict of properties of a compound from their molecular structure. It must be a structural invariant, means that every graph automorphism preserves here. These have been defined several topological indices, means last 30 years we have more than 10,000 topological indices are developed, and also last 10 years, more than 10,000 papers, more than every day, if you see the topological indices, many topological indices are introduced, and some of them are structurally connected with many compounds with respect to chemical indices. In that, here we deal with some of them. Some topological indices are classified, majorly we can classify it into degree based, distance based and neighborhood based. These are the fundamental properties of any topological indices can be developed. But mainly because the degree in a graph, any graph having a vertex and edge will be there. That is a simple concept we can utilize, and also we can study easily. That's why the degree based topological indices are many useful applications. Actually, topological indices are introduced in 1947 by Wiener index, that is introduced by Arnold Wiener. He not mentioned that his name, but he mentioned as a connective index. After some time in 1972, some of the mathematicians as well as chemists, they are named as that connectivity indices as a Wiener index. And also this is a distance-based topological index. It is useful in the isomers. After that in 1972, next slide, Gutmann and Resnick is independently looked out the alternative hydrocarbon total pi electron energy. They came across the term named as M1 and M2, that is known as Zagreb indices. After coming to the Zagreb indices, maybe more than 10,000 papers are published using the Zagreb indices. There are many applications, and not only mathematics, not only in chemistry, there are many biological as well as electrical circuits. They are utilized for this study. These are the two types of indices, Zagreb indices. Majorly, it is the many bigger molecular structures of compounds can be assumed. Combination of smaller units, long chain compounds are the typical example for the study. The studies of graphs obtained through different operation of simple graphs always keen interest researcher to the applied sciences. That's why I am very much confident that some of the younger researchers can first go through these basic papers, then you get many attractive as well as important applications related to this. Last year, 2024 and 25, we have many papers are published in this area, that is topological indices are more important in the area of research. This is one area, it is given a lot of application and many papers are published in the Q1 and Q2 journals also. Next slide. This is the first and second Zagreb indices we already mentioned, and Estrada in 1981 maybe, it is atom bond, he also introduced one more connectivity indices, that is atom bond connectivity, or we say that ABC index. You know that D of du and dV means the degree of the particular vertex, and dV is the degree of the another vertex. You know that how to find the degree. Degree can be find the number of connected vertices for that connected edges to the particular vertex. That is known as the degree of the vertex. Then similarly, the augmented Zagreb index, which is ABC index, and Fruzotova proposed the harmonic index, and Wolsnick and Gasparov introduced the inverse sum index. In 2001, there is a remarkable work done by Tresnikov and Gasparov in 90. They written two important papers, that is atom bond connectivity indices for 1 and 2. That is published by, there are 148, in the only two papers they are introduced the 148 atom bond connectivity indices. They are tested and also approved by the Iranian Mathematical Society. In that, this is one of them, that is inverse sum index. There are a lot of applications related to this, and many indices are there. Here I am highlighting some of them, whatever we taken for our study. Next slide. And next is some operation related to mathematical relationship. That's why we use some of the relations for operators. That is the operator we use. R graph is represented by, it is obtained by from H. There's another H is a subgraph. By linking a vertex V from V of H and corresponding to each edge, E is equal to UV belongs to E of H, and joining V to the end vertices U and V, that is known as the another edge. That is R graph. Similarly, we say that R vertex in similar way of R, and R edge and R edge neighborhood of a link graph. These are defined by early stages. Then these are some of the operators we are taken for our study. R vertex neighborhood and rooted graphs are the definition. These are some of the definitions. I cannot go through each and everything. And single edge connected graph and EV and V degrees. These are the some of the neighborhood related operators we have taken for our study. Next slide. Next. 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 Here there is a M polynomial. Let G be a graph. The M polynomial of G is defined as Gm of G is to x comma y. That is the summation of all the graphs. That is Mij is the number of edges of UV of G such that du means du and dv. You know that is a degree of particular vertex. Vertex degrees. Then we can calculate the degree of the produces the greatest degree based topological indices in M graph. Recently they introduced NM polynomial, that is NM of you can see that differences. That is we can take the neighborhood degree. Previously in the M polynomial we use the degree of the vertices, but in the NM polynomial we taken as the neighborhood degrees of some of the vertices of U and V. Next slide. These are the this is the tabulated version of some of the degree based topological indices derived from the M polynomial. That is first Zagreb, second Zagreb indices, second modified Zagreb, and symmetric degree division, augmented indices, general Randic index, ABC index, harmonic index, and inverse indices are in the first column. There are many indices. For our study, we are taken for this, and also the corresponding expression related to M polynomial of the topological indices in the that side, dx, dy, that is the derivatives. Next. Here, this is our SWCNT based carbon nanobud we are taken for our study. You know that the carbon nanobud structure has a fullness attached to the side walls of the carbon nanostructure. There exists a covalent bond between carbon-carbon atoms, fullerenes, and carbon nanotube. This additional fullerenes modifies some of the properties of the carbon nanotube. Carbon nanotube possess a good mechanical properties and electrical connectivity, whereas the fullerenes attached to the carbon nanotube restrictions movement of carbon nanotubes in the matrix material. As a result, the properties of final composites could be improved. The degree-based topological indices listed in the previous section you already known, and also M polynomial method, we can find the degree-based topological indices will help us to understand the dependency of the molecular structure on different properties of a graph. Here there are some general information related to the carbon nanotube, the chemical structure and chemical things, how it evaluated. Next. Now we can make a next slide. This is the Zagreb indices of R vertex and R edge link graph. The different link graphs, such as we already mentioned the definitions, R vertex link graph, R edge link graph, and R vertex neighborhood link graph. R edge neighborhood link graphs are obtained using the famous popular Zagreb indices, that is with respect to a M polynomial. A graph can be obtained connecting to the p number of fullerenes, because the simple graph we can calculate easily, but if you have taken a generalized structure, then the degrees may be changed. That's why we made a general structure with respect to the fullerenes of a single wall carbon nanotube using a single covalent bond. Here H is the representation of a graph whatever we obtained from the original graph. Using that, we can make a summation with respect to different types of degree base, the combination of the degrees, that is du and dv are the combination of that, means generally it containing 2, 3 and another one is 3, 3, the degrees depending on 2, 3, 3, 3 and 3, 4 and 4, 4 will be there. The edges, because we taken as a generalized version, that's why that is K we are mentioned, that is the generalized version of the edge set is 4K, K times 3n minus 2 minus 84p and 6p and p. These are the combination general p, q we are taken. Then after getting this the edge partition, we can apply to the m polynomial. We existed some of the results related to, next slide. The m polynomial of h, m1h and m2h be the first, second Zagreb indices we can derive. Means first you can make an edge partition set, then you have a m polynomial. Combination of that you can substitute and rearrange, you get these wonderful results related to m polynomial of h with respect to the carbon nanotube. That is the graph we have taken. Similarly, using this, I already mentioned how to, next slide. Using the above, this is the combination, the expression for the m polynomial expansion. With respect to that, we get the dx m polynomial of h, and similarly dx1 how we can calculate. Then similarly m1h is the combination of that and summation, you get the result. And also we can represent in the, we use the MATLAB, using MATLAB we can make a graphical representation of first Zagreb index of H. This is the thing, and similarly there are many results can be done using the Zagreb indices. Similar structure, we can do some more results related to the vertex, ring. There we mentioned many of the different operators, vertex, digger, and these things we done. Next slide. There are many operators we already mentioned for our study. We taken for the study, we get the m polynomial of first, second Zagreb indices, vertex degree, vertex link, and other links are also we can calculate. Similar way, whatever we given in the first theorem, similar way we can establish many theorems related to this. Next. Skip. These are some of the publication. The results are published in the Zagreb indices of link graphs related to carbon nanotube and fullerenes is published in the International Journal of Health Sciences in the last. It is accepted and it will be published shortly. And similarly, in the NM polynomial, we are computed m polynomial of nanostructure. This is m polynomial we already done. Then NM polynomials of cycle graphs, and also obtained some related topological indices. The evaluation of chemical and physical properties of nanomaterials are critical importance in a broad variety of nanotechnological researches. There is an increasing interest in computational method capable of predicting the properties of new and modified nanomaterials in the absence of time and consuming cost experimental studies. This is also, next slide. This is one of the carbon nanocone is taken for our study. And also NC is the molecular graph of nanocone. Observe that there are a number of edges, it is mentioned. Similarly, number of vertices and the degree sequences corresponding to the 2 and 3 is there. That is the NC, number of edges, and Kn square is the number of vertices. Next, using that, whatever we done in the previous, the same procedural way, we can apply to the M polynomial of molecular graph of nanobud. Relations are there with respect to M1, M2 and SDD and many more we are done. Here we showing some of them. That is the final results. And M polynomial of molecular graphs. Next, we move on to a NM because I am giving some highlights of the results related to M polynomial as well as NM polynomial. Next. Neighborhood degree polynomial, these are the NM polynomial structure with respect to the other indices. Whatever we taken, that indices structure with the tabulated with the topological indices with respect to NM polynomial. After getting a topological indices table, we can, after getting this table, we can find the standard graphs. What are the results related to, because we always mathematician, we check about our known graphs, that is standard graphs with respect to, next slide. We use wheel graph, NM polynomial for wheel graph and NM polynomial with respect to other indices. Same wheel graph, we check all the results. What is the generalized version of a NM polynomial for wheel graph with respect to all the topological indices. The procedural thing is same computational method for the checking the results is validated or not. Because whenever we validated things, first we can check the simple graph, then we can make to a generalized version, then you go on to a particular chemical structure. Then only you get the formalities will be finished. Next, and also we check about the Helm graph. Next, Gare graph. Next, this work is also published in the investigation of some topological indices of carbon nanotube nanobud through M polynomial. It is published in 2024 Indonesian Mathematical Society in that maybe in the volume 3. Next, NM polynomial. Next, recently in 2025, Deepashri is introduced because in 2021, Deepika and my team, one of our team researcher, he's worked on VL indices. That is the alternative version of a Zagreb indices. That is du plus dv plus du into dv. Instead of a first Zagreb index, she modified that index into a two structure with respect to a first and Zagreb indices. Motivated from the first and second Zagreb indices, she introduced the VL indices. Only introduction is not important, the chemical applicability of the VL index, she checked about the VL indices. After that, motivated from Deepika's work, that is the only degree based topological indices. That topological indices can be modified by Deepashri in 2024 with she introduced NVL index, that is the neighborhood VL index. That is introduced and it is in this fashion. You can observe VL indices with respect to neighborhood degrees, that is du, dv, here it is, she is mentioned dou v, dou e plus dou f plus dou e into dou f. Instead of replacing, that is du plus df, some rearrangement, and also the neighborhood degrees. That is the fundamental thing, and also the VL indices are useful in the octane isomers as well as PCBs. But here, This new index, next line, next. This new index is used in analysis of octane and as well as heptane isomers. The study shows the new index has a good correlation coefficient of more than 9 physical properties, ascent factor of octane as well as heptane isomers. Here we are highlighting some of them related to the correlation with respect to entropy, ascent factor, DHVP, and another HVAP, and many more. Next, because after she introduced about the neighborhood degree topological indices, she verified that this NVL index is useful for some of the chemical structure. Then, because we are mathematicians, we worked on the mathematical way. That's why we checked the sum of the bounds related to NVL index with respect to the maximum and minimum degree with respect to the NVL index. How it is, bounds are below and above, and related aspects are also we studied. And also generalized to the standard graphs, what are the relationship, because already some of the standard results are there. Simply we validated the some of the graphs related to NVL index, that is next VL Gare graph, and similarly Helm graph, and the another relationships are also mentioned. And after that, you know that bounds we verified the structural aspects, and we verified the bounds. Now we come across to the combination of the operators. We applied to the operator, different operators we studied. In the previous slides we mentioned some of the operator, that is R-link and R operator, we studied there. Similarly, here also we verified the Cartesian product, subdivision, tensor, because many things are there in the mathematical way. Here I am giving the highlights, not the general results I am mentioning here. Any students can opt and any work can be done. That's why, because it's a conference, is a generalized version. That's why I am highlighting some of the basics as well as the fundamental structures with respect to high dimensional things. Next slide. We constructed graph operation such as Cartesian product, subdivision, and tensor product, F-sum index of NVL index, and its bounds are also obtained. She worked on these areas related to with respect to NVL index as well as bounds with the VL index with respect to the edge with Cartesian product and other things. Next, VL index as well as NVL index, the relationship, how it will be changes. These things are observed. Many bounds related to subdivision. Skip the slides. Then, and Cartesian products, next. And the interrelationship between the previous indices are also mentioned. Skip some of the proofs. And this NVL index is also in the previous 2024 AIP conference is organized by Professor Defik. In the 2024 she presented and published with next slides. These results, some of the results related to Cartesian product, tensor product, and other relation. Next. These all the results are published in the AIP proceedings in the previous conference 2024. Next. All the results, many results are worked on that. And next is, finally, I will give some of the next slide. EV and VE degree topological operations in cycle graphs. We observed that tau is a corona product of cycle graphs of H1 and H2 having 2m Mn plus n cardinality of edges, Mn plus n cardinality of vertices with respect to edges, as well as vertex partition, edge partition you seen here, the many edge partition we can apply with respect to VE and EV degree of partition things, and with respect to the edge partition, these are the VE and VE degree and EV degree indices. Next, using that, we can calculate the EV degree based topological indices of corona product of cycle graphs with respect to Zagreb indices, modified Zagreb indices, and Randic index and EV degree of forgotten indices. Now, we have a scope for the new Nirmala indices and VL indices, VL neighborhood indices, and many things can be studied in this edge relation. These are some of the proof structure. I will skip because the time not permits us. These are the results. Move. These are some of the results related to Cartesian product and other things, vertex base, the procedure of the proof. You can skip. Many indices we studied, and rooted graph product with respect to EV and other things. Next. Next. Cardinality of it. These are some of the highlights we are giving here. This EV degree topological indices with the rooted graph product. Next. You can see many results. Many of the, I already mentioned, more than 10,000 topological indices are there. We use some of those who are studying for the topological indices, they can verify for the other topological indices also. Next, and single edge connected graph. Next, many results are related to this. You go to results. Next. These are some routine procedure you can adopt for the computation. Next. 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 This is the forgotten index with the delta and that relationship we are mentioned. Corona graph, rooted graph, vertices with respect to forgotten thing. Next. This is the another results, that is toroidal polyhex graph. This is the polyhex graph. And also you can study the combination of the EV degree and VE degree with respect to many results are also verified with respect to the subdivision graph of a toroidal graph. After the operation, what it happens, we also checked and verified for the results. These results also published in Monte Carlo Journal of Pure and Applied Mathematics in 2025. Recent results of some operation in cycle graphs related to EV and VE degree indices. The main paper is published in the recent version of the 2025. And after that, we studied its NVL index in 24 because our research group is working on temperature indices with respect to that temperature indices is introduced in 2021. After that, that temperature indices can be introduced with respect to VL indices and verified that temperature indices have a validated for many results related to isomers. After that, we checked in the phenyline nanotubes and also porous graphite are worked with respect to VL index. Now we are working on the NVL temperature index with respect to the many topological indices as well as the nanostructures and nanotubes. We are working in this current research related to temperature indices of nanostructures. Time is there? go to last slides. Go for last slides. Now we are checking the proximity index. Go for the last part. Proximity index is one of the important area for research. Now that M-level wheel graph we are checked. The generalized version of wheel graph is known as M-level wheel graph defined, and also M copies of cycle Cn connected with a common vertex such that all the vertices are adjacent in copies of Cn. That we worked on the related to proximity index of triangular oxide networks. We are worked on this research related to the indices, and also VL proximity index is defined, and also the results related to the generalized results are under process, and some of the results related to neighborhood proximity index are also studied in further time. The scope of the feature, scope of the feature work. Last slides. One not five. Here, these are some of the open problems that individual can carry in the future research work. The study of various distance-based topological indices. Not only distance, you can make for the degree as well as neighborhood degree vertices of nanocarbon structures or any chemical drugs. You can take whichever comes into the market, that you can check. First compare the results with the chemical structure, and upper and lower bounds for the proximity index based different graph operators. We are not checked till now. You can check for the proximity graph indices to study NVL index of molecular structure, different structure, carbon graphene, crystal carbon, cubic carbon structures, benzene ring, many more are there. You can also check, and QSPR analysis for the chemical compounds can be done, identify the useful topological indices. Many applications related to drug and compounds are also we can verify. And recently we are writing one book with Professors Kangul and our team working on the we have a project with respect to topological indices, writing 3 books in the Turkish university. One of the Turkish university agreed to make a book chapters for the next 2 years. There are through 4 volumes will be coming. Some of you are interested to make some work related to topological indices, work on that and send to us. We can validate and make it as in a book form for the topological indices. These are some of the important references for our study. Next. These are the fundamental books. Next. These are some, in this talk I given simply highlighting the combination between the topological indices. What is topological indices? What type of topological indices? Some of the operators and the combination of the chemical structures. Then we can mix with the chemical, mathematical and relationship. These are the fundamental things we given a highlights here in my talk. It may be useful to the future researchers for this wonderful conference. Thank you for giving an opportunity for telling some of my views related to topological indices. I especially thanks to Professor Udayana University and as well as Jember University people. They helped me come here and stay here with the Bali conference. Thank you very much. Thank you.
Thank you very much, Professor Lokesa, for the interesting presentation. Now we begin the question and answer session for participant here. You can raise your hand. For online participant, you can type in your question in the chat box and raise hand icon or and unmute the microphone. Please, maybe there is some question for participants. Okay, thank you.
Thank you. Yeah. Yeah, please.
Okay, thank you so much for your great presentation. It is a really compact presentation. My question is not a specific question related to your presentation, but this is about how to measure that some formulation of topology indices are good or not good. How to compare? Yep.
Yeah, actually, this is the basic theory, because here many mathematicians are present in this conference. That's why I made my presentation completely in mathematics version. Yeah. In the Jember conference, actually, I given the talk with respect to what previously we are used the correlation regression analysis, and we check if it is the validity of the topological indices with respect to chemical structure. We validated with respect to regression analysis. Very simple way, and it takes a rigorous version. Whatever we done, this takes more time for our mathematicians. Now we have using the ML models. Now we are make the 10 ML models for studying these topological indices. Those who are interested in data analytics and data science, we can apply these topological indices with respect to using Python codes. We already written Python codes. Now last 1 year, we working on that area, Professor Dafik, and we are jointly written one articles related to this chemical structures. We already done many structures because in my research group already produced 14 PhD theses related to topological indices. Manually we made many things. Now last 1.5 years we are working on machine learning and data analytics part. Then it is easy. Previously we are taken writing one paper and validation. It takes more than 1 month or 2 months. Now we will get it within 1 week or 2 weeks, because we write a code, it is established. And now last 1 year we check validation, because previous were and the machine learning things. This is matched. Now we will do some wonders if you know the machine learning operators. This is one important aspect. It is in the picture. Last 1 year, some Pakistan mathematician and China and US mathematician working in machine learning with respect to topological. And also in the last talk in the Zember conference, last 2 days before, I discussed I given a talk with respect to machine learning. That time Professor Dafik informed me about the graph and the combination. Because here I am not shown many graphs, but the graph structure, whatever the molecular structure is already present, because we transform to a graph, there is some of the carbon, except the carbon, other things will be vanished in the graph, general graph. That's why he mentioned that please make some embedding things or partition to, we can make a constructing the original graph. Because we are taken the 3 dimension to 2 dimension, some of the properties will missing sometimes. That's why we made the embedding, and also we can make in the supervised machine learning thing and rearrange. Maybe we will get wonderful results. That is under process. Actually, he mentioned, he commented or remarked. That is good comment he mentioned in the last talk. That is also under process now. Thank you for your wonderful questions.
Ya, pertanyaan selanjutnya.
Yeah, please.
Thank you for the chance. First of all, I want to say thanks to your wonderful presentation. The hardest question I've ever had is what is the application of your research? But you now you show us that topological indices branch in math has a lot of application.
Yeah, I've shown many things in the chemical, you see, in chemical analysis, as well as networking. Now we come across to the machine learning. There are many applications. Anything you can study. That's why last 1.5 years, this topological indices grown like anything within a span of time. It is in the Q1 factors journals, it is there now.
And I'm starting study the degree-based topological indices, especially degree-based topological indices of a ring, an algebra structure. But my result including series, a bounded series, and it doesn't look nice.
Pardon?
It doesn't look nice because it included series. I have read your article and
Statistical is very simple thing. Nowadays you can apply computer thing. It is very easy. The small, don't need the rigorous calculation of statistics. Basic fundamental calculus is, statistics is more than enough for studying this. Yeah. If you need any help, definitely you can contact. We will do, our research group is definitely help you.
Because when I read your article, the equation is look nice, but I
will send you the fundamental papers.
Yeah, but slightly, I think one slide has a long equation in your.
That is finalized version, because that is the stages. Because it's a conference, I given not simple things. Send you one link related to topological indices, the basic papers. I given basic lectures. That lectures I will share to any of you. You need, starting with a graph, each thing, step by step things are there. That I will share. Okay?
Thank you, Professor Lokesh.
Thank you. Maybe one more for the question. Participant here. Any question? Okay, I think it is enough for the first plenary session, for the first speakers. I give the conclusion for this presentation. This presentation underscore of the M polynomial, and M polynomial serve as engines for the generating a wide range of degree-based topological index Zagreb, ABC, harmonic, ISI, SGD, as well as NVL index across many graph classes, and carbon nanostructures such as nanobots and nanocones, including link graph variants, R-vertex, RH, RVN, and REN. And the talk presented closed form formula, upper and lower bounds, and behavior under graph operation, Cartesian product, subdivision, tensor product, and also F-sum. This indeed correlate well with the physico-chemical properties of isomers, aiding the screening of stable isomers, and the prediction of reactivity. In short, topological indices form a strong bridge between graph theory and the smarter, more efficient design of carbon-based material. Thank you very much, and give applause to Professor Lokesa.
Thank you. And also I make a special thanks to Professor Komang and Professor Dafik for making our collaboration in further, because our university rector, Professor Muniraju, day before yesterday, I called him to make one MOU with Udayana University. He is happily agreed with the exchange programs with respect to Udayana University and Vijayanagara Krishnadevaraya University of Ballari, India. We will make a more fruitful seminars, conference in future years. Thank you very much given an opportunity for this. Thank you.
Ladies and gentlemen, before we entering our next presentation, we will appreciate the keynote speaker by giving him certificate to Professor Vira Badraya Lokesha. The certificate will be delivered by Prof. Intan as President of the Southeast Asian Mathematical Societies. To Prof. Intan, please welcome. Thank you very much to Professor Lokesha for the fantastic presentation. This is your certificate as the keynote speaker.
Okay, now we continue to next presentation. Our second speaker is Dr. M. Venkatachalam from Kongunadu Arts and Science College. With 15 years of teaching and 11 years of research experience, his work centers on graph theory. He has supervised 9 PhD graduates and is currently guiding 4 scholars. Dr. Venkatachalam has authored 104 research papers, including about 70 in SCIE or Scopus Index Journal, and collaborates widely with scholars from Turkey, Indonesia, Morocco, the USA, South Africa, and also Spain. Dr. Venkatachalam, time is yours.
Thank you. Most Honorable Rector of this great institute, Udayana University, Bali, respected President of this Indonesian Mathematical Society, Professor Dafiq, respected President of Southeast Asian Mathematical Society, and Professor Homank, and Professor Suparta, and my dear friend and Professor V. Lokesha, and my dear friend Dr. Professor Ika Hesti Agustin, and my other fellow professors, research scholars, master students, and other participants. Very good morning to one and all gathered here. So really I am very happy to stand before you and deliver a talk on exploring equitable packing coloring in graph structures. Actually, in graph theory, graph coloring is the one of the main research area. There are a lot of areas. So, graph coloring is one of the main research area since it has wide applications in engineering, okay, as well as in the medical field also. Okay. So, today we are going to introduce some new graph coloring concept. Okay. So, myself and my scholar, Ms. Bharani, full-time research scholar in PhD mathematics, and my collaborating research team, Dafiq, Professor Dafiq, and his scholars. So, together we have identified a new concept, equitable packing coloring. So, I am very happy to introduce this concept firstly in a forum that is in one of the beautiful international conference organized by Indonesian Mathematical Society at Bali. Next slide. Celestin. The function eta is a surjective mapping that ensures that every vertex of a graph L, here we are considering graph, the notation is L, is assigned to a set of values from the color set C. Normally we are considering the positive integers for assigning the colors to the vertices. The colors start from 1, 2, 3 up to small l, satisfying in two conditions. For any two distinct vertices fg belongs to vertex set of L, graph L, if eta f and which is equal to eta of g equal to I, then the distance of fg must be greater than I. That is, the distance of any color I in a graph, the distance must be at least I plus 1. At least I plus 1. And also for any two distinct colors m, n belongs to C, such that mod eta inverse of m minus mod eta inverse of n, which is less than or equal to 1. This is the main conditions that the cardinality of any two color classes must be less than or equal to 1. Cardinality of any two color classes must be less than or equal to 1. A graph L with L coloring is called equitable packing coloring. The minimum L is equitable packing coloring chromatic number. So this paper establishes a new notion. The notation for equitable packing coloring is chi EP. Since chi P means that is already defined packing chromatic number, chi equal means that is notation for the equitable chromatic number. For our new definition, we are using chi EP for some basic graph of graphs. Next. Next. So as I said already, and these are all the basic things, the graph originating from the Euler's study of a Königsberg problem has evolved into a mathematical fundamental discipline for analyzing connectivity, optimization and resource allocation. So it is a key concept such as coloring, labeling and domination. These are all the main research areas in the graph theory. Pure mathematics, we are working on coloring. Sometimes we are working in the labeling as well as in the domination. Okay. So graph coloring is a fundamental concept in graph theory involving the assignment of colors to graph elements. So coloring means we have three types of coloring. One is vertex coloring, another one is edge coloring, and the third one is total coloring. So in coloring, we are using the main concept that is the proper coloring. Proper coloring means for proper vertex coloring, no two adjacent vertices having the same color. If two vertices are adjacent, we have to give the different colors. Similarly, it is the same proper coloring condition is applicable for edge coloring as well as the total coloring. Okay, next one. So as said, it has a main applications mainly in the computer science and operation research and etc. So Mayer et al., the reference number 13, introduced equitable coloring. Okay, there are two types of coloring introduced already in several years before, and there is a lot of papers published in the SCAE and Q1 indexed journals. Okay, the first one is equitable coloring, originally introduced by the Mayer as a variant of vertex coloring, where the size of difference between any two color classes is at most 1. So equitable coloring means there are two constraints. The first constraint is proper coloring, no two adjacent vertices having the same color. The second constraint is the cardinality of any two color classes must be less than or equal to 1. This is the two constraints for equitable coloring. Okay. So every tree is equitably delta colorable. Delta means here a maximum delta, this is the maximum degree. Okay. So ordinary chromatic number for any tree, the result is 2. For any tree, the chromatic number is 2. But in case of equitable chromatic number, it is increased. That is maximum degree. Okay. So in the next one, Kierstead and Hostocha in the reference number 12 gave a short constructive proof of Hygnal et al. In the reference number 9, stating that any graph G with the maximum degree delta can be equitably colored with the delta plus 1 colors. And Olario et al. In the reference number 14 discussed lower bounds for equitable coloring using an integer linear programming approach. Next one. And Goddard et al. In the reference number 7 introduced the concept of broadcast coloring. Okay. So the broadcast coloring, which was originally motivated by the frequency assignment problem in communication networks. In broadcast coloring, each vertex represents a radio station and the color assigned corresponds to a transmission frequency. The goal is to assign frequencies so that two stations using the same frequency are sufficiently far apart to avoid interference. The required distance between two stations increases with the power or frequency range of their broadcast. Next one. Why I am saying the broadcast coloring means the packing coloring is a modified version of broadcast coloring. So broadcast coloring is very much application in the frequency assignment. So similarly the packing coloring is also. So the packing coloring introduced by the Brisar et al. In the reference number 2, the packing coloring vertices of a graph represent transmitters while colors represent frequency levels. The coloring must satisfy the packing constraint. The packing constraint means based on the distance of any color I. So if you have two vertices receiving the color I means the distance must be I plus 1 at least. Okay. This ensures that two vertices with the same color I are placed at a distance greater than I, thereby preventing interference between transmitters of the same strength. Next one. So this is our new definition. That is combining or merging all the two constraints from equitable coloring as well as the packing coloring. So equitable packing coloring, EPC, by combining the principles of equitable coloring and packing coloring, we propose a new scheme called equitable packing coloring. Formally, an EPC is a subjective vertex coloring function. Eta is mapping from V of L to color set C, the values from 1 to L, satisfying the first condition is packing coloring condition. The second condition is equitable coloring condition. The first condition is assign the colors first and then the distance between any two color, the distance must be at least greater than I plus 1. The second condition is the size of, that is the cardinality of any two color classes must be less than or equal to 1. Both EC, that is equitable coloring, and PC, packing coloring, are NP complete in general. Next one. So this is the formal definition. So for instance, let G be a graph. Here we are considering one graph. Okay, to discuss about all the both ordinary chromatic number, equitable chromatic number, packing chromatic number, and as well as our new concept, equitable packing chromatic number. See the first graph. Here we have used only two colors. Okay. Here, ordinary chromatic number chi of G and equitable chromatic number chi equal to of G, which is equal to 2. Since we have used only two colors in the first graph. In the same graph, packing chromatic number is 4. Since, if you consider any two color, here if you use the color as integer means you can easily understand. Here the packing chromatic number is 4. Next one. So here, equitable packing chromatic number. So here, this vertex is a critical vertex. Why I am saying the critical vertex means, here for this vertex we must assign the new color 5. Otherwise, only 4 colors are enough for packing chromatic number. Only 2 colors are enough for equitable chromatic number. Only 2 colors are enough for ordinary chromatic number. But in the case of equitable packing chromatic number, we have 5 only because of this vertex. Okay. So here we can say this is chromatic number condition. Proper coloring also satisfied this graph, and equitable chromatic coloring conditions also satisfied, and the packing coloring chromatic number concept also satisfied, and our equitable packing chromatic number concept also satisfied. So for this same graph, the equitable packing chromatic number is 5. Here if you consider, if you take 2 is here and 2 is here, and the distance of these two vertex is 1, 2, 3. That is, distance must be I plus 1, that is 2 plus 1, at least 2 plus 1, 3. So here 3 is here. Similarly, you can consider any two same color assigned the vertex. You must have distance at least I plus 1. Okay. Also, here we are using the color 1 for 2 times. That is color class of, cardinality of color class 1 is 2. Cardinality of color class 2 is 2. Cardinality of color class 3 is 2. Cardinality of color class 4 is 1. Cardinality of color class 5 is 1. So, any cardinality, that is difference between any cardinality of any two color class is here less than or equal to 1. So equitable condition also satisfied, packing coloring conditions also satisfied. So here our new concept achieved. Okay, next one. The graph G admits chromatic number and equitable coloring with the 2 colors, packing coloring with the 4 colors. However, its equitable packing coloring requires 5 colors. This increase occurs because the critical vertex violates the equitable coloring condition. Consequently, an additional color must be assigned to the critical vertex to preserve the equitable property. Next one. Now we are based on this concept, we have proved some lemma results theorems. The first lemma is for any graph G, the following inequality holds. Always the equitable packing chromatic number of any graph G is greater than or equal to maximum of equitable chromatic number or packing chromatic number. A proof, let C of K denote the set of all proper K colorings sub G. Define the following subset. The equitable chromatic number is contained in C of K, and the packing chromatic number is contained in C of K, and the equitable packing chromatic number C of K, which is equal to C equal of K intersection CP of K. Here C, that is equitable condition, represents the set of all equitable colorings, and the CP of K represents the set of all packing colorings. By definition, an equitable packing coloring satisfies both the equitable and the packing condition simultaneously. Hence, it lies between the intersection. That is intersection of packing and equitable coloring. Next one. Therefore, the equitable packing coloring contained in that is the equitable packing chromatic number containing equitable coloring, and equitable packing coloring contained in packing coloring. If chi EP, that is equitable packing chromatic number of G is equal to K, then there exists an equitable packing coloring using K colors. Therefore, equitable packing chromatic number is not equal to empty set. From the above inclusions, it follows that both equitable chromatic number and packing chromatic number are also non-empty sets. Hence, equitable chromatic number of any graph G is less than or equal to K, and packing chromatic number of a graph G is less than or equal to K. Since K equal to equitable packing chromatic number of G is the least integer for which such coloring exists, we obtain equitable packing chromatic number of any graph G is greater than or equal to maximum of equitable chromatic number or packing chromatic number. Next one. Next corollary. So this is a very important one. The equitable chromatic number and the packing chromatic number are not comparable in the general. Okay. Sometimes for a same graph, equitable chromatic number is high and packing chromatic number is less. In some other graphs, sometimes packing chromatic number may be high and equitable chromatic number is maybe less. Okay. So next one. So we have, this is in this case, in mathematics we know, for not true case we have to give one example. For true means we have to prove the result. If not true means we can give one example, it is enough. So see this example. So this is a bipoded graph, that is K1, 3, or we can say this is a star graph. Here, the first graph, see here. Here K1, 3. Here we have used 3 colors. That is chromatic number for this graph is 3. The leaves are pairwise at distance 2 greater than 1. So this is a valid packing 2 coloring. Hence packing chromatic number of this K1, 3 is 2. Any proper 2 coloring of K1, 3 has color sizes 1 and 3. See here. Here this is, we can say here this is equitable of K1, 3, this is 3. So see here, this is the packing. Packing of 1, 3, that is 2. Okay. So equitable chromatic number of K1, 3 equal to 2, which is greater than 2. It is the packing chromatic number. Next one. So this is equitable P4, path with 4 vertices. Here equitable chromatic number is 2. Okay. Packing chromatic number of P4 is 3. Okay. Here packing chromatic number is greater than equitable chromatic number for this path. So in general, we cannot compare for any particular graph. In general, both equitable chromatic number and packing chromatic number. Sometimes packing will be high and equitable will be less. Sometimes equitable will be high and packing will be less. Next one. So these are all some basic graphs, family of graphs. So the equitable chromatic number for these graphs already published, and the packing chromatic number of the same graphs already published in the reference number 15. These results published in the reference number 11 and 16. So equitable chromatic number of path equal to 2. The number of vertices must be greater than or equal to 2. Equitable chromatic number of cycle with the q number of vertices, it is equal to 2 whether the number of vertices is odd, which is equal to 3 which whenever the number of vertices are even. Same the complete graph, the equitable chromatic number and the ordinary chromatic number, that is the number of vertices, as already we know the basic concept. So kq means it is q, and for wheel graph this is the floor function of q by 2 plus 1 whenever the number of vertices must be greater than or equal to 4. Similarly, this is the star graph k1 comma q, the floor function of q plus 1 by 2. Here q is must be greater than or equal to 2. The Helm graph, the number of the vertices denoted by q, which is equal to 4 whenever the q is odd, which is equal to 3 whenever q is even. Also for every q greater than or equal to 4. Similarly, the closed Helm graph, which is equal to 4 whenever the number of vertices must be greater than or equal to 4. So gear graph, which is equal to 2, the number of vertices whenever for every q greater than or equal to 3, and complete bipartite graph, which is equal to 2. Similarly, in the packing chromatic number for path, which is equal to 2 whenever q equal to 2 comma 3, which is equal to 3 whenever q greater than or equal to 4. Similarly, for cycle, which is equal to 3 whenever q equal to 3 or 4 slash q, and the for remaining graphs the result is fixed by 4. And for complete graph, which is equal to q. For complete graph, the equitable chromatic number, packing chromatic number, ordinary chromatic number all are same. Okay. For wheel graph, it is floor function of q by 2 plus 2. And for star graph, which is equal to 2, Helm graph, which is equal to q plus 1, and closed Helm graph, which is equal to q plus 3, whenever the number of vertices are odd, whenever number of vertices is even, the result is q plus 2. For gear graph, the result is 4, and for complete bipartite graph, the result is q plus 1. Next one. So this is the application of equitable coloring in scheduling ICC Cricket World Cup. Okay. So already we have developed some algorithms and prepared on a nice paper along with the DEFI group and published in the Q1 journal already. And scheduling ICC Cricket World Cup involves multiple constraints. No two matches involving the same team can occur in the same round. The number of matches per round must remain nearly equal. So our contribution is, in our recent work, myself and along with DEFIC and others, okay, the paper published in the last year, 2024, we have mentioned in the reference number 17. An iterated modified double search algorithm we have proposed. The tournament was modeled as an equitable coloring problem where vertices represent matches, edges represent team conflicts, and colors represent rounds. Next one. So, iterated modified double search enhanced, that is a double search algorithm. Iterative backtracking dynamic parameter updates and probabilistic search mechanisms. So outcome of this work ensures a balanced and conflict-free schedule, guarantees that no team plays twice in the same round, reduces total tournament days and operational cost, provides faster and high-quality solutions than traditional methods. Next one. Next one. So, here one simple application for our new concept, that is packing chromatic number and equitable chromatic number, our new concept, equitable packing chromatic number. Here there are 5 transmitters denoted by capital T1, T2, T3, T4, T5 in a network. Interference constraints, that is edges connect interfering transmitters. Here T1 is adjacent with T2, T2 is adjacent with T3, T3 is adjacent with T4, T4 is adjacent with T5. We have assumed like this. So step 1, the packing coloring is assignment without equitable constraints. That is for T1 we are saying F1, for T2 F2, for T3 F1, T4 F3 and T5 F1. Next one. Here see here T1 assigned 3 times. That is, we have a 3, if F1 is heavily assigned and F2 is only 1 time and F3 is only 1 time. This is not a equitable chromatic number, since equitable constraint is violated. That is, here as per our observation, frequency F1 is heavily loaded for 3 transmitters, while F2 and F3 is assigned only once. Okay, next one. So the second one, equitable packing coloring. As per our new concept, here F2 is assigned 2 times. For F2 is assigned for T1 and F2 is assigned for T4. And F3 is assigned for T2 only. And F1 is assigned for T3 and F1 is assigned for T5. Here F1 assigned 2 times, F2 assigned 2 times and F3 assigned 1 time. So here clearly this is the condition of equitable chromatic number validated, and as well as the condition of packing chromatic number is also validated. So therefore our new concept, whenever if you using the equitable packing chromatic number, next one, the balanced load occurred. Okay, so fair frequency utilization. As per our new definition, each frequency is assigned to a similar number of transmitters. Load balancing also good, avoids overloading any single frequency, improved quality of services, reduces the interference and ensures reliable communication. Next one. So these are all some preliminaries for consider our new, this is the mathematical work. Okay. So the first one is the wheel graph. The wheel graph is obtained by joining a central hub vertex E to all vertices of a rim cycle, and it is taken from the reference number 10. And the Helm graph is constructed from a wheel graph by attaching a pendant vertex En double dash to each rim vertex En dash. It is available in the reference number 8 and 18. And the star graph is obtained by joining a central vertex E to all leaf vertices E1 dash, E2 dash, etc. Es dash. Next. Similarly, the fan graph is formed by joining every vertex of a path E1 dash, E2 dash, etc. Et dash to the hub vertices E1, E2, etc. Es. The closed Helm graph is obtained from the Helm graph by joining the pendant vertices attached to the outer cycle vertices En dash to form a cycle. The flower graph is formed by adjoining the central vertex E adjacent to all En, that is inner cycle, and all En dash, that is the pendant vertices. Similarly, we have a gear graph is obtained by subdividing the rims of the wheel graphs by the vertices En dash. Next. Similarly, the front sheep graph is obtained by arranging an OR complete graph K3 with vertices En around the hub vertex. Similarly, the book graph consists of T copies of K3. K3 means, as we can say, sometimes a triangle sharing a common edge spine EF. For the nth triangle, let the additional vertices be En and F1 adjacent to EF respectively. Similarly, we have the complete bipartite graph. They are obtained by arranging M vertices En and T vertices Fn into 2 independent sets, with each vertex En connected to the every vertex Fn. Next one. So based on these definitions, already we have taken a new results equitable packing chromatic number for these basic graphs. Since while introduce the new concept, always we are considering some basic family of graphs. Now working for the general upper bound and some results for general graph, and also the graph products are under pipeline. And the theorem for any S, that is number of vertices here denoting by S is greater than or equal to 4. The equitable packing chromatic number of the wheel graph is which is equal to 4 whenever S equal to 4, which is S minus 1 whenever S is greater than or equal to 5. So this is the proof. So for proof we are using the diameter. Okay, to prove we is using the number of vertex, that is a concept of vertex set and the diameter. Next one. Here the diameter is 2S minus 2. Here normally we are using, first we have proved both upper bound and lower bound. Okay. So for S equal to 4 means this the proof is very simple. Assign the color for E equal to S and for En dash equal to N, and N varies from 1 to S minus 1. If S greater than or equal to 5, assign the color functions like this. Thus here for all the vertices we have assigned the equitable packing coloring. So the result is less than or equal to 4 whenever S equal to 4. The result is less than or equal to s minus 1 whenever s is greater than or equal to 5. Next. So this is a lower bound proved. Next one. That is, no, previous slide. Previous slide? Yeah. See. For lower bound, we consider two color classes, so two cases. Case 1 s equal to 4 and case 2 s greater than or equal to 5. We have here diameter of WS is equal to 2, and by packing coloring condition, the only color that can be assigned to more than one vertex is color 1. Suppose we assign color 1 to the first floor function of s minus 1 by 2, odd indexed, that is odd indexed rim vertices, then satisfies the packing coloring condition. Every other vertex must receive a distinct previously unused color. Hence, each color other than 1 appears exactly once. We cannot assign more than 1. Now by the equitable coloring condition, color 1 cannot occur more than twice, since all other colors assigned one time. So color 1 we can assign one time or two time. We cannot go for more than 2, since otherwise the equitable chromatic requirement would be violated. Therefore, combining both conditions yields the standard lower bound, okay, which is greater than or equal to 4 whenever s equal to 4, which is s minus 1 if s is greater than or equal to 5. So this is lower bound, already proved upper bound. So equitable packing chromatic number of any wheel graph is equal to 4 if s equal to 4, which is equal to s minus 1 if s is greater than or equal to 5. Next one. So this is a example. Okay, wheel graph with 8 vertices. Okay, always consider the hub vertices, that is 1, and the rim vertices 8. So 8 plus 1, 9 vertices. See here. Here in the bracket we have assigned the color. Here we have assigned the color 1, 2, here again 1. If you consider these two, the packing coloring conditions, the distance must be at least 2, so distance is 2. So here we cannot assign color 2, since 2 means here 2, the distance must be at least 3, but here we have distance only 2. So here we cannot assign 2, so we go for 3. Similarly, here we cannot assign color 2 or 3 or 1, so we assigned 4, 5, 6, 7, here 8. So here equitable packing chromatic number of wheel graph with 9 vertices, which is equal to 8. So as per our results, here the number of vertices is 9 minus 1, 8. So as per our theorem, this is the example also matching. So result is s minus 1 whenever s is greater than or equal to 5. Next one. So for any r greater than or equal to 4, the equitable packing chromatic number of the Helm graph is, which is equal to 2r minus 1. R is number of vertices. Next one. So this is the Helm graph with the 7 vertices. Here we have assigned the color 1. Okay. So here we have previous one. Here we have assigned 2, 3, 6, 7, 2, 8, 3, 1, 9, 10, 6. So here the result is 10. Previous slide, previous. 7 means result 10. So 7 means 2 into 7, 14 minus 4, 10. So whenever r equal to 7, our result must be 10. So go to the next slide. So here I got 10. Okay. So next one. So for any t greater than or equal to 2, the equitable packing chromatic number of the star graph is given by t. Okay. Next one. See the star graph. Here assigned 1. No, previous slide. Here assigned color 1, 1, 2, 3. Okay. Here also we can, for ordinary chromatic number, we can assign 1 here. Okay. But it violates the packing chromatic number. Maybe it is also equitable chromatic number, since here assigned 1 for 2 times. Here 2, 3, 4, 5, 6, 7, 8, 9. All other colors are assigned 1 time. And color 1 is assigned 2 times. So the any 2 color class, cardinality of any 2 color class is less than or equal to 1. So here equitable constraint also validated and packing constraint also validated. So equitable packing constraint both are validated. The result is equitable packing chromatic number of star graph with 9 vertices, which is equal to 9. Next one. So next theorem. For any s greater than or equal to 1, t greater than or equal to 2, the equitable packing chromatic number of the fan graph is given by 3. Whenever s equal to 1, t equal to 2. Otherwise, the result is s plus t minus 1 for the remaining cases. Next one. See, this is the, here we have 4 vertices. Here we have 12 vertices. The result is 15. Okay. So here 1, 1, 2, 3, and then 4, 5, 6, up to 15. So this is the example. Next one. So for closed Helm graph, whenever the number of vertices greater than or equal to 3, the equitable packing chromatic number of the closed graph is given by 6 whenever the number of vertices equal to 3. The 2h minus 1 whenever h lies between 4 and 7. The same graph which is equal to 2h minus 2 whenever h greater than or equal to 7. Okay. So next one. So this is the whole closed Helm graph with the 9 vertices. The result is 16. So 16 assigned here in the hub vertex. And see here 1, 2, 1, 3, 2, 4, 5, 6. And here 7, 8, 9, 10, 11, 12, and 13, 14, 15. And 16 is assigned here. The result is 16. Okay, next one. So for equitable packing chromatic number of flower graph is given by 2L. Okay, next one. See here we are using the 13 number of vertices. That is 2 times into 2L. That is L is equal to 13. 2 into the 13, 26. So this is the results 26. 26 is assigned in the hub vertices and all other colors assigned in the outer. Next one. For any graph h greater than or equal to 3, the equitable packing chromatic number of the gear graph is given by, which is equal to 5 whenever h equal to 3, which is equal to 2h minus 2 for other cases. Next one. So this is the example. Gear graph with the 10 vertices, the result is 18. So 18 is assigned in the hub vertex. Here we have assigned 1, 2, 1, 3, 10, 2, 11, 3, 12, 4, 13, 5, 14, 6. 15, 7, 16, 8, 17, and 9. Here you see the color cardinality of any two color class is less than or equal to 1, as well as if you consider the color 13, here assigned 13. Okay, so here we have assigned 13 only one time, so the distance is only 13 is there is no other 13, so we cannot consider. And if you consider 1, color 1, here also 1. So the distance must be at least I plus 1, 2. So distance is 2. So both the packing constraint and equitable constraint both are validated. So equitable packing chromatic number is 18. Next one. So for any t greater than or equal to 3, the equitable packing chromatic number of book graph is given by, that is bt means that is 2t. The number of vertices into 2. Next one. So this is the book graph. The result is 18. So here also you can verify both equitable constraint and the packing constraint. Both are validated. Next one. So next for friendship graph, the result is 2R. Next one. See here, friendship graph with the 6 vertices, the result is 2R, that is 2 into 6, 12. So 12 is assigned in the hub vertex and 1, 3, 8, 4, etc. Next one. For complete bipartite graph, the result is k m comma t m plus t minus 1. Next one. See here for there are 2 vertex set in the complete bipartite graph. Here in the first vertex set we have 4 vertices. In the second vertex set we have 7 vertices. That is 4 comma 7. That is 4 plus 7 minus 1. That is 4 plus 7, 11 minus 1, 10. So we have assigned 10 colors here. Here also both equitable and the packing constraints both are validated. Next one. So next we are coming to the conclusion. So this is a very new concept. The concept of equitable packing coloring of graphs open up for a press and promising direction in graph coloring research. blending the balancing constraints of equitable coloring with the distance-based restriction of packing colorings. The study established rigorous results by determining the equitable packing chromatic number for selected graph families. Here we have considered some of the basic graph families. Also we have derived the new results and we have proved everything and prepared a research paper as well. And demonstrates how this parameter captures a richer level of structural complexity compared to earlier coloring models. Future research aims to extend these investigations to find the other graph classes and graph products, and we are also trying to give some algorithmic aspects of equitable packing constraints and explore potential applications in frequency allocation. So there are a lot we can, by using this packing equitable constraint, we can apply this concept and find the variety of applications, the frequency allocations, network partitioning and other optimization contexts. Next one. So these are all the references. So see here, he is introduced packing coloring, and this is a very famous journal, Discussions Mathematica Graph Theory, published in the 2020, and Discrete Applied Mathematics, Packing Chromatic Number, Cartesian Products. And this is our paper in equitable coloring alone. And this is chromatic index almost, that is published, and circular chromatic number of flower graphs. Here they are using flower graphs. Next one. So here they are finding the equitable total coloring. So they verified the equitable condition for both vertex edges, that is total coloring. And so this is broadcast chromatic number, that is like packing chromatic number. This is published in the Ars Combinatoria. And this paper having the Helm-Graph concept. This is published in the Linear Algebra and Applications. And they have published. Okay, next. For basic graph definition, you can use the graph Harare. And these Kaliraj and Bernard Lewin, they have published equitable coloring of Helm-Graph and Gare graph, which is published in International Journal of Mathematics and Combinatorics. And see this in the other papers. And this is my scholar Rajalakshmi and myself. Rajalakshmi completed her doctoral thesis in the only packing coloring alone. She has derived more than 100 results in the packing coloring. She has completed already the research. And this paper is published in the Journal of Discrete Mathematical Structures and Cryptography. This is a Q2 journal published by the Taylor and Francis. Next one. And S.K. Vaidya and Isaac, that is, they also published equitable chromatic number of some wheel-related graphs. And myself, this is my another scholar, Bravina. She also completed her thesis. We, along with our Professor Defik and Gangul from Uludağ University, Turkey, we have used iterated modified double search for equitable coloring and scheduling cricket World Cup tournament. So this is also a very good journal, Journal of Science and Engineering, published last year. And this is my another colleague, Vijayalakshmi and Kalaivani. They have published dominator coloring of sunlit gear and Helm graph. Here we can take the definitions of sunlit gear graph and Helm graph families. Next one. So thank you. Mathematics is the language which God has written the universe, Galileo. And as per my wish, I can say something. In the world, we have three types of languages. The first one is human language, the communication between person to person. Okay. For example, Tamil, English, and Indonesian language, Russian language. These languages are using for communication between person to person. Here, domain also person, codomain also person. The second one is machine language. That is communication between person to machine. There are several languages, C, C++, Python, Java, etc. And the third one is logical language. That is mathematics. So mathematics is a logical language. So if you know logical language, you can do anything. So once again, I thank our Professor Defik and Komang and other personalities for giving me an opportunity to deliver a talk in this IndoMS International Conference on Mathematics and Applications. Thank you, one and all. If you have any questions, you can ask now.
Thank you very much, Dr. Venkatachalam, for interesting presentation. Now we begin the question and answer. Any question for participant here? And for online participant, you can write in the chat box. Yes, please.
Okay, thank you again for the moderator.
Yes.
And thank you for great presentation.
Okay, thank you.
It is really interesting for
Yeah.
me especially.
Yeah.
Is there any characterization of graphs such that the chromatic number of equitable coloring and chromatic number of packing colorings are the same?
For complete graph?
Pardon?
Complete graph?
Complete graph. No more graphs?
No more graphs, we have to check.
Okay. Just because maybe I am wrong.
Yeah.
In my opinion, if we have graphs having the same, what we call, chromatic number of equitable.
Only I think complete graph only equal. For other graphs, maybe either equitable chromatic number may be high and packing is less. So for some graphs, packing is high and equitable is less. We cannot compare both the equitable and packing chromatic number in general.
Yep. Yeah. You mentioned already.
Yeah.
But whenever they are the same, I don't know, is the chromatic number of equitable packing colorings is the same as the value of that chromatic number. Is that correct or not?
No.
No, okay.
No. Equitable packing equitable chromatic is greater than ordinary chromatic number, greater than equitable chromatic number, greater than packing chromatic number.
Okay. So no equations.
Yeah. Always greater than.
Okay, thank you so much.
Okay, thank you, Prof. Nanga. Any question? Disilakan kepada Bapak Ibu, mungkin ada pertanyaan lagi. Okay. Next, I will give a conclusion. This talk introduced equitable packing coloring, synthesis of equitable and packing colorings. It established sharp results for multiple graph families, namely flower, gear, book, and also complete bipartite graph, and etc. with explicit coloring and matching bounds. Equitable packing coloring captures structural complexity than earlier models and open direction for border classes and so algorithmic aspect. On the application side, equitable packing coloring is pertinent to scheduling and frequency allocation illustrated by the ICC Cricket World Cup scheduling with equitable coloring and iterated modified tabu sets balancing loads while minimizing conflicts. In short, equitable packing coloring provides a robust bridge from graph theory to the real world optimization. Thank you very much. Give applause to Dr. Venkatachalam.
Ladies and gentlemen, before we entering our next presentation, we will appreciate the keynote speaker by giving him certificate to Dr. Venkatachalam. The certificate will be delivered by Prof. Intan as President of the Southeast Asian Mathematical Societies. To Prof. Intan, please welcome. Thank you very much to Dr. Venkatachalam for the fantastic presentation. This is your certificate as the keynote speaker.
Plenary session 1 has concluded. Thank you to our speakers and all participants for your attention. Now I proceed over to the next moderator, Professor Nengah, to lead the following session. Wassalamualaikum warahmatullahi wabarakatuh. Salam Om Swastiastu, salam kebajikan dan salam sejahtera untuk kita semua.
Ladies and gentlemen, a very good morning. And in the third presentation, we will have talk from Professor Komang Darmawan. He is from Udayana University, Denpasar. Oh, sorry, tiga ya. Oh, so sorry. Oh, sorry. Sorry, I was thinking that the third presenter is Pak Komang, but actually Bapak Safruddin. Yeah. Okay, I would like to read some of his experience in terms of scientific experience. Di sini nggak ada ya? Nggak ada ya? Oh iya ya. Ada anunya? CV-nya nggak? Ya, oke. Ya. Prof. Safruddin is from Mathematics Department, Universitas Negeri Makassar. So sorry about this because I just got his information. And he has some scholarships for finishing his study and some research which have already published. And so there are many publications published by Prof. Safruddin. And what else? And his specialty, I think, is on mathematical modeling, differential equation, numerical methods or simulation, including statistics and their application. And the title, no title? Okay. Sorry, the title of his talk today is CC Modeling with RK87 to explore local wisdom in combining climate-induced dengue spread through Wolbachia factors in southwest Sulawesi. So it is related to health. Yeah. I think that's enough for introducing Professor Safruddin. Now the floor is yours. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And good morning, ladies and gentlemen. Thank you, moderator, for giving time to me. The Honorable, the President of ASEAN Mathematical Society, Prof. Intan. Selamat datang di Bali, Prof. The President of Indonesian Mathematical Society, Prof. Dapik. Thank you for giving chance to me to participate participate in this conference, IICMA. Chairman of this conference, all participants, offline and online. Today, I would like to presentation about our research in the mathematical modeling. This is the little different with the before, because this is the focus, the how to using the mathematical, like the graph, like the ordinary differential equation. Sorry. Slideshow, please. Okay, the title of our research is the CZ modeling with Rengkuta 8 and 7 to explore local wisdom in combating climate-induced dengue spiritual Wolbachia vectors in West Sulawesi. We have two proponents to improve this modeling in the South Sulawesi and the West Sulawesi. Next, please. Okay. This is the introduction or the information about the dengue fever. Dengue fever remains a major public concern in South and West Sulawesi, Indonesia. There are many cases in two provinces, more than 1 million cases, the number of cases in the South and the West Sulawesi. Dengue fever is caused by dengue virus transmitted by Aedes albopictus and Aedes aegypti mosquitoes, and is characterized by symptoms such as high fever, severe headache, and in severe cases. Next. This is the data, how many cases dengue fever in Indonesia from the 2021 to 2025. In the 2021, we have many cases, and then 2022, there are 70,100 cases, and the peak of the cases of the dengue fever in Indonesia in the 2024. There are 250,100 cases. There are many cases in Indonesia. In the 2025 until August, we have 67,000 cases in Indonesia. Next. This slide explains about the dengue cases progression, 3 times higher than same period in the 2023. This data explain about how to explain how many cases in Indonesia of the dengue fever, and the total of the number of cases is the 250,000 cases. And the next slide explain about the fatalities progression, highest mortality rate in ASEAN region. This slide explain about the highest mortality rate in ASEAN region, and Indonesia is the highest cases in the of the dengue fever disease. And the next slide explain the case fatality rate, how many percentage of fatalities among confirmed cases in Indonesia. And in the slide, we can see how many cases of the case fatality percentage in 2025. There are 0.44%. And the next, also the data from the how many cases in Indonesia of the dengue fever case. And this slide explain about the incidence rate and the case fatality rate in Indonesia, start from the 1968 to 2023. Next, this is just a little information about the dengue fever disease. In Bogor, there are 4 people died of the dengue fever, and there are many information, many news about how many people to be died after the dengue fever disease. Next. So after the information, our team to find the problem about the dengue fever disease, and then try to how to find the solution about the problems. And we have a research objective, start from the how to make the how to find the collection information about the transmission modeling of the dengue fever. And the first step, try to make the modeling mathematic, how to find the modeling mathematic. This one, the modeling is a SAIR-CC. SAIR-CC for this model, including the parameter climate, biology, and epidemiological. And there are 3 analyses of this model. The first is how to find the equilibrium point. The second is how to get the information about the stability of the model. And the last, how to find the R0, the basic reproduction number. The basic reproduction number is very important to find, because this one explain about how many cases if one person to be infected by dengue fever, and we can transmit it to the other people. Okay, and the second is after we find the model, the analysis, and try to find the solution of the model using the numerical method. There are many methods to find the solution of the model, like the Rank-Kutza method, homotopy perturbation, iterasi parameter variation. We have many methods to find the solution of the model. And after that, the next step is the validation strategy. How to fill a validation, data comparison, parameter rename, and then the last of the problem is a policy output. The policy output is the recommendation how to find the solution of the dengue fever in Indonesia. And the special for our research is how to find the solution for dengue fever disease in South Sulawesi and West Sulawesi. And the local integration in this research, not only to including of our model climate, but also including to how to traditional knowledge to control, to be the control factor, and also cultural assessment to adding for the model and find the solution. Next. This is the roadmap or state of the art of our research. Start from the SIR model of dengue fever in the West Sulawesi. There are SIRS and SAIRS model for the dengue fever transmission in Sulawesi. Also, we find the model for COVID-19 split, and the online gaming addiction, the population density poverty level analysis in Makassar, SEI model for malaria, and 2 years, start from the last year, we find funding support from the DICTI to make a modeling CC dengue with climate, Wolbachia, local wisdom, and fogging. So next. This is the novelty of our research because there are many research about the climate change, Wolbachia, and local wisdom, but there is not combining of 3 parameters yet in the one model. So the novelty of our research is a combining of 3 parameters including to one model. One model is a model for dengue fever disease. Next. This is the research level technology. So now we have the level technology 3 and for the next year we would like to submit a proposal again to change for the next step like the applied research, modeling, prototype, and patent. Next. Next, please. Okay, this is the research methodology. Start from the how to conducting literature review and collecting historical data. And the second step is model development. And the third step is stakeholder validation. And the next is a final simulation. And the next is output finalization. And after that, we can make the recommendation for the hill government in South and West Sulawesi. Next. This is the result of our research. Start from the how to find the CC model. This is the formulation of the model. There are many variables and there are many parameters in this model. I think if we see this slide, there's a very complicated model. And after that, we find the modeling formulation. Of course, the model is the ordinary differential equation. The system nonlinear of ordinary differential equation. Next. This one is the formulation model of our research. We have 1, 2, 3, 4, 5, 6, 7. We have 7 variables and we have many parameters to find the solution of the model in dengue fever disease. Next. This one is the data. How to find the data? Start from the how many people in the Sulawesi, how many people in the West Sulawesi, and find the data from the pusat statistik. And also we find the many data, many primer data from the questionnaire, and also we find the data from the Department of Health 2024. And after all of the data to be completed, and next. Okay, we find the model analysis. The analysis of the model are three parts. The first is equilibrium point. Equilibrium point divided by disease free equilibrium and the endemic equilibrium point. Next. And the second is how to find the stability of the model. The stability of the model find from the agent values. If all the agent values are negative, the CCC model is asymptotically stable. And the last is find the basic reproduction number. Next. The basic reproduction number according to the data is the R0 is 0.25. Because R0 less than 1, this indicates no sustained spread. Means infected individuals cannot influence other individuals to become infected with dengue fever disease in this scenario. But the government must to make the strategies to find the solution of the transmission of the dengue fever disease in Sulawesi and the West Sulawesi. Next. This is the demonstration that says CC model. According to the figure in this slide, we can see in the figure, if all intervention in the model and given the impacted population is many slowly. If all intervention including in the model and giving the solution, because impacted population to be slow and decrease. But we can see the blue color, if Wolbachia and local wisdom including only Wolbachia and local wisdom including in the model, and we find the solution of dengue fever disease is a very high. That means all intervention need to combining in the model. Next. This is the airship control and intervention scenarios. For example, times required of airship control, all intervention, if only Wolbachia and local wisdom, there are many cases, but the others to be decreased. And the second figure, how many, the number of the basic reproduction number. For example, if all intervention including in the model, and we have the number of the basic reproduction number is 0.191. But if only pogging including in the model, and we have the basic reproduction number is 0.323. Okay, next. This is the CIRSI model analysis using the Renkuta method. But the previous slide explained about how to find the solution of the model, how to find the basic reproduction number, analysis, the model, but this step, how to find the solution using the numerical method. For this one, find the solution using the Renkuta 8 and Renkuta 7 method. Once again, there are many methods in the numerical, in the mathematics, like the Renkuta. We are the method iterasi parameter, and also we have the homotopy perturbasi, Adams-Moulton, but our research for this part special to find the solution of the model using the Renkuta 8 and Renkuta 7 method. According to the figure for this slide, we can explain about the red color is the Renkuta 7. The green color is the error. Is the error of the Renkuta 8 and Renkuta 7. Now, according to the slide, there are many, just a little error from the two Renkuta method. That means Renkuta 8 and Renkuta 7 is better to using for the find of the solution of the dengue fever disease. Next. This is the comparative analysis of simulated and real. We have the real data and find the how to comparing about the real data and after the simulation of the Renkuta model. This one explain about that on January until the August on 2025. Sorry, there are a typo. Okay, next. CIRSI model prediction of the spread of dengue fever. There are many figures for the last simulation of our research, like the figure 1 explain about the dynamics of suspected human and recovered human for if local wisdom, Wolbachia, and fogging, including of the model. And the second one is the dynamic of the exposed human and impacted human if climate, local wisdom, Wolbachia, and fogging, including of the model. In the figure explain about only need just a few time to be decreased of the dengue fever disease if all the parameters including of the model. But next, if we have three parameter including to the model like the climate, local wisdom, and Wolbachia, this slide explain about that. For the suspected human, recovered human, exposed human, and the impacted human. Impacted human is very important to explain for this session. In the red color, explain about the impacted human if three parameter including of the model, climate, local wisdom, and Wolbachia. There are a very high need need to be high for the 1 year. Okay, next. This one also explain about three parameter including of the model. The three parameters are climate, Wolbachia, and fogging. And this figure explain to the dynamics of the suspected human, recovered human, exposed human, and infected human. Okay, for this, the right side of the figure explain about the need only 1 year to be decreased of the number of infected cases of the dengue fever disease. Next. Yeah, this is the same explain about that. And the next. Okay, this slide, this figure explain about if only two parameter including of the model, namely climate and fogging, need 1 year to be decreased of the number of cases of dengue fever disease. Next. Okay, I think the same. Just explain about the dynamic of recover human. Next, please. Okay, and the conclusion of this research is the combining strategy of Wolbachia-based biological control and local wisdom within a mathematical model is highly effective to suppressing long-term dengue transmission. And the second one, without intervention, exposed and impacted cases are projected to rise continuously over 2 decades. With the combined intervention, the basic reproduction number are 0, falls significantly below 1, less than 1, indicating the disease eradication is theoretically achievable. Sensitively analysis in the 5 key drivers. Biology and climatic factor are the primary drivers of disease spread. And the last conclusion, the study concludes that an integrated approach combining high order numerical methods, ecological insight, and culturally adapted strategies is essential for effective dengue control in tropical region, climate sensitive region. Next. Okay, this one of references of our research. This is all of the publication is our team. We have 2 publication in the Q1 and the others Q2 and Q3. This is the output of the supporting funding from the Kementerian Dikti Saintek in Indonesia. Next. And the last is the recommendation of how to doing for the future research. The first is integrate real-time climate and epidemiological data, strengthening local wisdom integration, enhance Wolbachia deployment strategies. We can also estimation parameter of all our model. This is the statistics, and maybe we can adding the other parameters to the model if need. And the last is also we would like to submit proposal for this year in the scheme of the applied research. And the output of the applied research is the model, prototype, and patent. I think enough for me. Thank you very much. Thank you, moderator.
Thank you, Pak Syarifuddin, for your interesting presentation. Now we are entering a new session, question and answer. Is there anyone who wants to pose some question, both in offline mode or in online mode? No question yet? Just one question. Yeah, while waiting for... yes, Pak Komang, please.
Okay, thank you very much. In your research, did you try to prove the uniqueness of the solution? And then what I quite don't understand about the control, object function control, or the control. Can you just explain shortly?
Okay, thank you so much for your question, Pak Koman. Jadi the last research about the COVID-19 and publication in the CHEOS Q1, special for how to make the optimal control of COVID-19 transmission. But for this one, just a little difference, because this is the focus to find also the first find the modeling of the dengue fever disease. But after that, our team to find the very unique to find the for three parameter. This parameter like the climate change and also the Wolbachia. I think in our mind, Wolbachia can be special case to control optimal of the dengue fever disease. Jadi dari tiga parameter itu kita mencoba untuk memikirkan bahwa Wolbachia nanti akan menjadi bagian spesifik untuk membuat model ini dengan menggunakan kontrol optimal. Because if choose one of the parameter like the Wolbachia for the to control of the model, I think the formula of the ordinary differential equation system to be different.
Thank you, Pak.
Thank you, Pak Komang. There is one question.
Yes.
There is one question online.
Oh, sorry. Yeah, please. Yeah.
Okay. So thank you so much. I'll read first in Indonesia, okay, Pak?
Yes, okay.
And then try to translate in English. Yeah. Model matematis apa yang digunakan untuk menguantifikasi dampak dari kearifan lokal sehingga dapat dimasukkan sebagai parameter atau fungsi di dalam model CRCC? That's the first question. So this is about asking a mathematical model in what we call translating local wisdoms into mathematical variables. And the second one, apakah model tersebut dapat mengidentifikasi sebarang kearifan lokal yang memiliki dampak besar terhadap pengurangan kasus dengue jika dibandingkan dengan intervensi Wolbachia. So about the accuracy of the model in translating what we call it the local wisdom parameter into mathematical parameter. And the third one, bagaimana model secara spesifik memodelkan peran komplementer dan penting dari intervensi berbasis komunitas dalam memastikan keberlanjutan atau sustainability and partisipasi publik. Is there any specific model for
Iya, langsung dijawab.
this role? Yeah.
Ya, terima kasih. Thank you so much for your question.
This question is coming from Denny Hamdani.
Oke, terima kasih Pak Hamdan dengan 3 pertanyaannya. Yang pertama adalah bagaimana atau model apa yang pas dengan memasukkan unsur kearifan lokal, Pak ya? Ya, jadi kalau misalnya untuk kearifan lokal juga harus dipertimbangkan matang-matang kalau misalnya sudah ada model itu, kearifan lokalnya masuk di mana? Ya, for example, 2 tahun lalu kami melakukan penelitian tentang kearifan lokal mengenai amotere abaji. Jadi di kalangan Bugis Makassar ada istilah amotere abaji. Dalam hal ini adalah kasus silariang. Jadi karena tingginya uang panai di masyarakat Bugis Makassar, beberapa pasangan memilih untuk lari bersama dengan calon istrinya dan menikah di tempat lain. Nah, ada kearifan lokal yang coba dikembangkan yaitu amotere abaji. Artinya dia kembali dalam keadaan baik-baik dan melapor kembali ke orang tuanya. Nah, itu kearifan lokalnya. So, how to build the local wisdom to be the model, including in the model. Jadi model ini akan melihat apakah dengan adanya amotere abaji ini bisa menekan jumlah kasus silariang di masyarakat Bugis Makassar. Berarti dia klop. Nah, kalau misalnya dikaitkan dengan including in the model about the dengue fever disease, kira-kira di mana kearifan lokalnya masuk, itu berarti untuk menekan banyaknya di samping Wolbachia ya, intervensi Wolbachia. Nah, kita bisa masukkan kearifan lokal itu misalnya ketika ada masyarakat tertentu di daerah tertentu membuang sampah sembarangan karena sumber dari penyakit dengue fever itu adalah adanya nyamuk Aedes albopictus dan Aedes aegypti, di mana ada yang hidup di dalam lingkungan rumah dan ada yang di luar. Nah, ketika misalnya dia membuang sampah sembarangan, maka jentik-jentik nyamuk untuk yang hidup di luar itu akan tumbuh sehingga muncul kearifan lokal. Misalnya kalau misalnya dia membuang sampah sembarangan dan ditemukan, maka dia akan didenda misalnya dengan apa begitu. Nah, itu masuk kearifan lokal dan intervensinya masuk ke dalam perubahan dari exposed menjadi impacted, because step of the exposed to impacted human of the dengue fever disease, we have one intervention parameter intervention in there. Ya, jadi harus ada intervensi ketika misalnya sudah menimbulkan gejala, lalu kemudian untuk menekan banyaknya yang menjadi tertulari, maka ada intervensi. Nah, intervensi itu bisa masuk, salah satunya adalah kearifan lokal. Itu barangkali. Kemudian pertanyaan yang kedua tadi mungkin sudah terjawab langsung Pak ya, yang tadi di mana dimasukkan. Nah, lalu untuk menjaga sustainability.
Yang pertama itu ada proses kuantifikasi. Is there any quantification
yes,
process?
Of course.
Okay.
Ya, jadi pasti ada proses kuantifikasi, apalagi namanya literature review, and after that kita we find the conclusion this local wisdom is better including in the model or not. Ya, jadi harus ada kuantifikasi dulu sebelum menyimpulkan dia akan masuk sebagai intervensi atau tidak. And the last, how to bagaimana menjaga sustainability of the model dengan adanya kearifan lokal ya, tentu saja dengan melihat hasil the result of the simulation of the model. Kita punya banyak di IT, ada Maple, ada R, yang bisa kemudian MATLAB yang bisa membantu kita menemukan ternyata kalau intervensi dari local wisdom ini dimasukkan, maka nanti jumlah the number of the dengue fever case in Sulawesi misalnya to be decreased. Berarti perlu dipertahankan atau sustainability-nya perlu dijaga. Tetapi kalau misalnya there is no impact of the local wisdom in the model intervention, I think kita akan try to change the other parameter to find the solution of the dengue fever disease. Seperti itu, Pak.
Okay, thank you.
You're welcome.
Yeah, hopefully Denny is satisfied with the answer of our presenter. And the next question is from Prof. David.
Thank you very much. Yeah, studying mathematical modeling as well as solving by numerical analysis is a little bit quite complex. If you would like to go further into an application, sometimes we try to focus about the real world. But somehow we can say that it is very hard to get a good publication if we do not have an ablasan study. An ablasan study meaning that we need to explore which specific numerical analysis that you use. In this case, you use Rankuta of order 7 or order 8, for example. In fact, we already have the built-in MATLAB software for the Rankuta, ODE 45, ODE 23, even my student also already done Rankuta of order 12 or something like this. Do you have any ablasan study to know the convergent history and numerical effectiveness of solving the ordinary differential equation? A part of Rankuta, for example, you develop by yourself about the method, because we have plenty of methods like Adam Batsford, Adam Moulton, multi-step, of everything we have already there. Yeah, but sometimes if you go to a top tier journal, we need to have like a new methodology, new method for solving the ordinary differential equation, which is very complex. Thank you very much. Yeah.
Thank you so much for your suggestion, Prof. David. Yeah. Actually, Rankuta 8 and Rankuta 7 in this research, actually only to support or modeling and giving the this one giving the solution of the model. But we also try to find the solution for the last year using the Rankuta 15 method, but just a mathematician. Jadi kami sebetulnya sudah punya itu menggunakan MATLAB atau menggunakan Rankuta, but kami belum mau betul-betul menggunakan itu karena secara matematik we have to try the learning deeply learning how to find, sebab ini yang bekerja dalam mesin dan kita sebagai orang matematik harus paham dulu sampai di mana the steps to find the Rankuta 16. But thank you so much for your suggestion, karena memang kalau mau levelnya kayaknya ini cuma kemarin kami sampai di Q2 di reject, jadi kami coba lempar di Q2 yang lain. Saya rasa salah satunya adalah pembuktian untuk membuktikan datanya itu hanya menggunakan RK 8 dan 7, harusnya sudah menggunakan RK 15, RK 16. Sekali lagi thank you so much for your suggestion, Prof. David. Nanti kami akan mencoba menggunakan the new methodology and the other Rankuta.
Okay. Unfortunately, we are restricted with time, and the QA session is closed. Now we are going to conclude actually, although the conclusion is already clear, that Pak Safruddin proposed a new method, which is a combination of two methods actually, SAIRS and CC model, supported by Rankuta 8 and 7. And in that model, he considered many parameters like climate vectors, Wolbachia, and then community local wisdom, and many things. So thank you so much for interesting presentation, and I would like to ask all participants to give applause again to his
Thank you so much.
presentation. Thank you so much. Thank you so much.
Ladies and gentlemen, before we entering our next presentation, we will appreciate the keynote speaker by giving him certificate to Prof. Syafruddin. The certificate will be delivered by Professor Dafiq as the President of the Indonesian Mathematical Society. To Prof. Dafiq, please welcome. Thank you very much to Professor Syafruddin Side, SSE, MSE for the fantastic presentation. This is your certificate as the keynote speaker.
Okay, now we are going to continue with the fourth presenters, and the title of his talk is a semi-parametric hybrid of Gompers, Richards, growth and Gaussian process regression for Bali-Kettle body weight prediction. So this talk will be delivered by Professor Komang Darmawan. He is from Universitas Udayana, Bali, Indonesia. And I think we already know that he already published some papers in some what we call qualified journals. And according to Sinta index, his Scopus index is 8 and Google Scholar H index is 11. Prof. Komang, the floor is yours.
Thank you very much. Okay. First of all, I would like to thanks to Prof. Dafiq for inviting me to present in this event. And then Prof. Starto, thanks for your collaboration during this event. And then Prof. Intan, my colleagues in ITB. And then Prof. Lokes, thanks for your initiating a collaboration with us at the University of Udayana. Yes. Okay. At this time, I would like to present my research funded by the University of Udayana, which is the title of my research is a semi-parametric hybrid of Gompers or Richard growth model and Gaussian process regression for Bali-Kettle body weight prediction. Okay, let me explain a little about the semi-parametric. In this research, we use parametric, which is Gompers and Richard model, and we use also non-parametric, which is the Gaussian process regression, and then we combine. We call this hybrid, the term, and then semi-parametric and non-parametric. If we combine, we call hybrid, semi-parametric hybrid. Okay. In this presentation, I would like to give a mathematical formulation, the theory, how we get the theory and theorem, how to prove the uniqueness, the asymptotic, and then the existence of the model. Okay, and then we try to predict the body weight using the available data. Okay, we work together in this research with Peri Swastika, Putu Peri Swastika, from my department, and then Sarini and Oka from the husbandry department, and Professor Budi Nurani Ruhiana from the Pajajaran University. Okay, this is the talk outline. First of all, we describe the background, motivation, and aims, and then we try to review a biological short review about biological growth submodels, and then next semi-parametric hybrid formulation, and then this is the theory, assumption, identifiability, existence and uniqueness, and asymptotic. Okay, research methodology, and then application to data, and result, discussion, and biological interpretation, and conclusion. Okay, why do we need the precise body prediction? Okay, this is actually we need for support the feed management, nutrition planning, optimal marketing windows, and genetic selection. Next, how do we approach this data or phenomena? Where as the very old model, we use the Gompertz and Richard. This model is very interpretable, but underfit complex data. And then we approach as well the data by machine learning method, which is random forest, gradient boosting machine, support vector machine, and deep neural network. And then this is achieve high accuracy, but less interpretability. Yeah, biologically less interpretability. Okay, that's why we need a trade-off between the interpretability and the flexibility. And then we propose the Gaussian process regression, which is offer a powerful framework in capturing the nonlinear dependencies and quantifying uncertainties. This is the motivation, and then this is the hybrid model. We estimate the MT theta. This is the from the parametric, and then GX. This is non-parametric. G come from the we call the reproducing kernel Hilbert space correction, and then G is a member of the K, kernel K. Next, this state of the art, I guess, quick review, and then here classical model, Richard, and then we balance between interpretability and rigidity, and then there is recently there is spline and general additive model, and then next hybrid modeling and advanced, very advanced recent work, most of the modeling using this model. Okay, the last here in this slide we present the research gap of the research is a unified semi-pragmatic theory that rigorously defines additive and multiplicative hybrid. Okay, I am of the research to formulate unified semi-parametric hybrid, and then to establish identifiability, prove the existence and uniqueness, and then try to find the consistency and symptomatic normality. The third, to construct the profiled estimation algorithm which convergence guarantees, and also incorporating Gaussian hyperparameter tuning. Okay, the last one is to benchmark predictive performance. Jadi using root mean square error, mean absolute error, and square root. This is the review why Gompertz model still considered to be used, because the biological interpretability, which is we can estimate the asymptotic or the weight, the maximum weight of the cattle, and then we also know the growth rate of the cattle, and then time of inflection. Okay, this is the properties. We skip this one. Okay, next we also apply the Richard model, which is the generalized of logistic model. Similarly, this model show also the asymptotic weight and the growth rate, time of inflection, and the last one for this model we have a shape parameters that can control the asymmetry. We call the the parameter nu. Okay, this is special case. Richard model will become the special case when we take nu is nu equal 1, and then which is become a logistic model, and then we approach the zero from the right limit, and then we have a Gompertz curve. This is the inflection point of this model. Okay, the flexibility of this Richard model, because there is additional parameters, which is new, allow control to curve asymmetry. Now, what kind of hybrid we apply in this data? There are two additive hybrid model, which is the sum between the parametric and the non-parametric sum. And then we also do multiplication for the M and H using log ratio. Okay, as we explained before, GH in this model is come from the non-parametric correction in the reproducing kernel Hilbert space. Yeah, or we HK induced by the kernel K. Okay, let me explain a little about the additive hybrid model. The additive form, this model can capture systematic residual structure across morphometric data. And then, but for the multiplicative form, this can handle the size-dependent variability, where the residual variance scale with body weight. Okay, we also use the penalized estimation criteria. Okay, when we, in this model, we estimate the theta g. Let's say example, the g is we can choose G from members of element of Gaussian regression or the reproducing Hilbert space. The first term here, the first term here is measure the residual sum square between observed and predicted body weight, and the second one, the second term, it is the RQHS, which is the reproducing kernel Hilbert space penalty, controlling the smoothness of G and mitigating overfitting. Okay, by representative theorem, we can claim that theta is the minimizer in G, where the G can be represented as this is like linear combination of kernel function. Now, with this model, we alternating between update update theta and G iteratively until converge. Jadi we alternating or we optimize and update theta, the parameter of the parametrics, and the G, the function. For example, we can use the Gaussian regression function. Now, what's the equivalence between reproducing kernel Hilbert space and Gaussian process equivalence? These two actually equivalent by lambda, taking lambda as a sigma square and theta square, tau square. Now we use also the kernel ridge regression, which is equal to Gaussian process posterior mean, while GP posterior covariance quantify predicts uncertainty. Okay, this is the mean and this is the variance of the F or G. Okay, let me explain shortly the assumption. M, which is the has a second derivative on this interval t theta, and compact theta, capital theta. This is the in space RP, and K is the kernel is continuous, positive definite, and then bounded. Is bounded, and then the outer multiplication in average is convergent to the we call this the covariant matrix. Okay, the error we assume also have identical independent distribution with covariant proxy sigma square. Okay, let me continue the meaning of identifiability and consistency intuitively. Okay, we analyze the model in both additive and multiplicative or using log ratio scale. Okay, again, we show this, we have presented this before. Now, identifiability, that means that the solution of the function, solution is unique, and then we can differentiate it. We can differentiate it from the other solution with the same data. Okay, and then we also use the this condition ensure the composition of into mechanistic and non-parametric part. Okay, in the paper we prove also the theta is the square root of n consistent. That non-parametric prediction rescale is normal lambda over n is the kernel of the effective dimension. Okay, this is the, we call the well-posed penalized problem. Under the three assumption, and for any lambda greater than 0, the penalized objective unique minimizer for estimating the theta and g. Moreover, by representer theorem, we can represent the g estimator as a linear combination of the kernel. Oh, this is the assumption. Let me explain that when we add the data, when the data is bigger or growing, and then the model will converge to the theta 0, the parameter, and with the square root n consistent. This is the asymptotic regulation. Now we go to the profiling alternating estimation. We use the machine learning. Our objective here to estimate the semi-parametric hybrid model for body weight prediction. On this example, we use data age t, which is the days, and then morphometrics, body length, body height, and heart girth. The heart girth is circumference of the cattle body. Okay, and then this is the very technical processing. We standardize non-age covariate, and then we do initialization. We obtain theta 0 from linearly square. Now we use on our simulation, we use the Gaussian process fit. And then we found that this we excluding the age first, and then we combine the age after we do the simulation. And then we update the growth parameter. This is actually the Gauss normal. This is very the standard in single linear function, non-linear function. This is the we call it is quite similar to Newton-Raphson method, where we estimate the parameter, where J is the Jacobian, the matrix Jacobian. And then for the applicative model, we replace y by log y. And then hyperparametric tuning stopping time, and then model selection. Okay, the time is going too fast. This diagnostic criterion. Okay, This represent that we combine age, kernel of age, and the kernel of the morphometric body measure. And then here we sum, and then this we combine it. This is the kernel. And then we use the kernel of automatic relevance determination. We call the method 5/2. Okay, and then we do the calibration also, and then we evaluate the model uncertainty using 90% coverage. And we do also cross-validation with 5-fold. And then next, happy parameter tuning and featuring selection within fold. The last one is decision rule. Okay, this, I think we skip this one. Okay, this is the data, empirical data, morphometrics data of Bali-Kettle. We have age in days and body weight Y kilogram, and morphometric covariate X, which is body length, height at wither or body height, and heart girth, which is body circumference. Okay, processing. First, we as usual, we remove the outlier and do standardization, and then do prediction. Okay, let me move this. This is the model we use. We apply to the simulation. We use the Richard estimation model, and then we combine with Gaussian process regression, which is G, and then this is the error. And this the additive. This is for multiplicative, we use this model. Okay, this is the result from Richard model. We have this is our data. And then the data is only female cattle, female Bali cattle. It is about 398 data. Our result is, if we use direct Gaussian process regression, we have the root mean square error is 13.060, and hybrid model Richard is nearly the same, and then it's similar. We can say this is similar, even slightly better for the direct Gaussian process regression. But when we use hybrid, we still have the biological interpretation. So if you use the direct, we only have the estimate. We don't have the biologically behavior of the or biological characteristic of the cattle. That's why hybrid is good for choosing when we manage do management of the nutrition or feeding management. Yeah, because we know the asymptotic, the maximum weight, and then from the model. Okay, the result. This is if we use the Richard and compares, this very only 64%. This we call the underfit. Okay, interpretation and implication. Okay, we know fixed sigmoid form fail to capture the residual heteroscedasticity. And then hybrid succeed, combine mechanistic interpretability, and then we use the characteristic of the body weight, and then the flexibility from the estimation. Jadi this is the hybrid. This is succeed of the hybrid. Practical impact for precision livestock management and breeding use direct GPR. Best accuracy, and then for hybrid model, balance of interpretability and performance of the prediction. Okay, the growth characteristic of Bali cattle, we don't need this one. Let me skip. We continue to. Okay. The conclusion. Hybrid modeling succeed, and then integrating the mechanistic growth law and Gaussian process regression. Second, profiling, alternating estimation ensure efficient joint optimization of parametric and RKHS component. Theoretical guarantee establish identifiability, existent uniqueness, and asymptotic. Okay, this conclusion that I have, and the most important thing is the practical implication, and then we have precise livestock management, and to support feeding optimization. And acknowledgement, and this is this research is funded by the LPPM Udayana University under Senior Academic Research Grant, and then Department of Pajajaran University. We also discussed with this Professor Budi Nurani. We also thank to Balai Pembibitan Ternak Unggul, Hijau Pakan Ternak, BPTU HTP Denpasar. Thank you for your attention.
Okay. Question and answer. So no question yet. One question, please. You can go to the mic.
Okay, thank you, Prof, for the opportunity. I'm Devni Primasari from Universitas Negeri Padang. The model combine a parametric approach such as Gompers or Richard, and non-parametric approach such as Gaussian process regression. How does the prediction result of Bali cattle body weight differ between additive and multiplicative combination? They differ of result.
Okay.
Thank you.
I think I explained before, and then multiplicative is approach can capture the biological characteristic such as the asymptotic and the what's called the time of inflection of the growth. That's why my result on this table before, it is the multiplicative. So the my conclusion is multiplicative is better than additive form, because they can capture the biological characteristic of the body weight or body growth, sorry.
More question? Okay, Prof. Did you try to what we call to measure how accurate is your model
An application.
comparing with similar models which are already founded?
Okay. As I said before, we do model using machine learning like deep learning, and we use also the random forest, and then the hybrid model is better. The result is quite the same, similar, but hybrid model give more information like biological growth, times of inflection, and then asymmetric body growth. Yeah.
Okay, thank you. Yeah, I think no more question because of the time actually. And now we are going to conclude the presentation of Prof. Komang Darmawan. This presentation introduced a semi-parametric hybrid growth model that combines biologically interpretable curves such as Gomez and Richards with a flexible Gaussian process or RKHS correction, so that cattle body weight can be predicted more accurately while still reflecting the real biology of growth. This framework is statistically well-founded with identifiability, consistency, and uncertainty qualification, and it supports real application in precision livestock management, including feeding decision and genetic selection. Okay, thank you so much for a great presentation, and I would like to ask all participants online and offline to give a big applause to Prof. Darmawan. Thank you so much. Thank you, Prof.
Ladies and gentlemen, before we entering our next agenda, we will appreciate the keynote speaker by giving him certificate to Professor Komang. The certificate will be delivered by Professor Davik as President of the Indonesian Mathematical Society. To Professor Davik, please welcome. Thank you to Professor Komang Darmawan for the fantastic presentation. This is your certificate as the keynote speaker. Thank you very much to our four honorable keynote speaker for this session. Professor Vira Badrayah Lokesa, Dr. Ven Katachalam, Professor Dr. Syafruddin Side SSI MSI, Professor Komang Darmawan for the fantastic presentation. And also Dr. Ika Hesti Agustin SSI MSI and Professor Dr. Inengah Suparta MSI as the moderator. The next agenda is break for lunch and praying. The presentation by the next keynote speakers will resume at 2 p.m. in Central Indonesian Time. We kindly ask all participants, both offline and online, to return promptly to the same location or the Zoom link. Thank you. Agenda berikutnya adalah waktu istirahat untuk makan siang dan sholat. Presentasi dari keynote speaker berikutnya akan dilanjutkan pada pukul 2 waktu Indonesia Tengah. Kami mohon kepada semua peserta, baik offline maupun online, untuk kembali tepat waktu ke lokasi atau link Zoom yang sama. Terima kasih. Okay. Prof. Simsek, are you hear me?
Excelsa.
Yeah.
Good
Prof.
morning. This is
Good morning.
Professor Jangul.
Yeah.
We have changed the slots with Professor Simsek. We talked last night due to
Yes,
some
brother.
problem.
Brother.
Yeah.
Brother, yes, I understood. Excelsa. Now, Professor Nasi Changgul turns. Professor Simsek already
Good morning, Professor
confirmed
Nasi.
after, Professor Nasi Changgul. Yeah, Excelsa, yeah.
Okay. So, Professor Ismail Naci Canggul first, and then followed by Professor Ilma Simsek.
Yes, yeah.
Okay.
Thank you.
Okay. We can start, Professor Canggul.
Yes.
Okay. Good afternoon, ladies and gentlemen. My name is Elsa, and I will be your moderator for this plenary session. I hope you had a refreshing lunch break and are now ready to continue with our conference. Before the presentation begins, let me inform how the presentation will be going on. First, the keynote speaker will be invited to present about maximum 40 minutes. After that, there will be a Q&A question just like 5 minutes. Okay, let us now begin with the first speaker. Yeah. Welcome, Professor Ismail Naci Cangul from Bursa Yildiz University, Turkey. Hello, Professor. How are you?
Thank you, Excelsa. How are you?
Oh, I'm fine, thank you. Okay,
Nice to see you all again.
nice to see you, Professor. Okay, I will introduce Professor Dr. Ismail Naci Cangul is a professor at Bursa Yildiz University. He completed his PhD at the University of Southampton, UK in 1994. His research focused on number theory, algebra, graph theory, and mathematical analysis. He has authored over 370 papers and several books, and he has been invited to speak at numerous international conferences. And Prof. Changul has supervised many graduate students and received several academic awards for his contribution to the field. Okay, Professor Ismail Naci Changul, are you ready to present your presentation?
Yes, thank you very much for nice introduction. I would like to tell my best wishes to all participants, and I'd like to thank Professor Dafik, Professor Slamin, Professor Subarto, you, Ika, Venkatachalam, Lokesha, all the people that I know very well. For the invitation and for including me to this nice meeting. So today I will talk about in the last few years, I've been working on this and I have applied this omega invariant to many problems that my friends all know. I've been working with your group, with other groups, with my students here. So it became a nice topic, over 60, 70 papers, some theses, including one Indonesian thesis as well about omega invariant. So it's becoming very popular. Today I will give you a slightly different talk than a few days ago, but the main topic is the same. So you will all know if you have listened this one. The main theme is the same. So let me try to continue if I can. Yeah, I can control it. Some problems I shall talk about graph theory. Maybe before starting the talk, I shall give you 1 or 2 minutes about the borders of graph theory, because every day in many general journals, not only graph theory and combinatorics, graph theory is becoming more and more popular and having more place in number of pages, in terms of pages. So some of the graphs are some of the journals are becoming graph theory journals, in fact. So why graph theory is so popular? Because there are lots of problems. At the first sight, they are looking very easy, like Fermat's last theorem, which is the very important theorem which couldn't be proved for over 3 centuries, but it was looking very easy to a primary school student even. So these graph theory papers are dealing with problems on applications of graphs, graph parameters like distance, like degrees, like energy, like domination, like chromatic number, like independence number, this kind of parameters. Also topological indices, over 4,000 of them. Also derived graphs, also graph operations, graph products. So these are having a lot of applications. So not only mathematicians, but also chemists, industrial engineers, city planners, pharmacologists, they are working on graph theory and they are having papers more and more every day. So it's becoming very popular. If you are looking for a topic to study for your future, graph theory is a nice area. So I chose this way about 15, 16 years ago. We started with some papers at that time, and in the last 15, 16 years, we had a lot actually. The problems today I shall be mentioning are the below ones. For example, you are given a set of integers starting y1. A1 times 1. This is not a set, this is a multi-set. This is a sequence actually, because there are multiple items. The same item more than one cannot be appearing in a set. So this is a multiple set, multi-set. So this is A1 times 1. This is the number, the multiplicity of the degree, okay? So A2 times 2, A3 times 3, and delta is the largest vertex degree, and this is its multiplicity. So think that problem. You are given some numbers, some integers, 1, 1, 1, 2, 2, 3, 6, 10, 15, something like this, okay? The problem is, can you draw a graph having these numbers as vertex degrees? Very basic problem. For example, if your vertex degree is 3, then your vertex should have something like this, 3 edges meeting at this vertex, okay? So this is an easy idea, but no one can guarantee a way to these problems. The first one is easy. It's about the realizability of sets of integers I will be mentioning in a minute. So the first one has at least 10 algorithms to solve the problem. The first one, the main one, is Havel-Hakimi process, for example, since 1950s, 1960s. So this is not too difficult. We can decide whether we can draw a graph having these vertex degrees. This is okay. But main problem is how many graphs can be drawn. We have been working on this problem for over 3-4 years now. We have partial relations results for some graph classes, for some degree sequence classes. But in general, we have not solved. If we can solve the general problem, then there will be many open problems answered. How many graphs? Yeah, this is very important. And the third question is the cyclomatic number, well known cyclomatic number, the number of independent cycles, non-overlapping cycles in the graph, closed faces, the number of closed faces. So this is not known for a set of integers. If you have the graph, then you can count it, it's easy. But for a set of integers, there are lots of, maybe thousands of graphs, and it's difficult to decide about their number of faces. Are they different? Are they the same? Of course, different. Another question, what is the cyclomatic number? This time, realization having C components. The previous problem was for connected realizations, only one unique piece of vertices and edges, connected one. Transversality is there. But in the fourth one, cyclomatic number of a realization with C components. For example, the problem is, given a degree sequence or given a set, can you draw, or in how many ways you can draw such a graph with 3 components, for example, or 5 components if possible. We don't know yet. So the next problem is about the number of components. What is the minimum and maximum number of components amongst all realizations? There are lots of realizations in general, and what is the minimum number of components amongst them? Of course, the minimum number could be 1, at least. 0 component is not possible because at least one vertex forms a component. That's easy. So the minimum number, natural lower bound is 1, but sometimes we cannot have connected realizations. That's another problem. If we cannot have connected realizations out of this set, then we have realizations having at least 2 components, 2 different parts, or 3 components, or 4 components at least. We don't know. Okay? So, the last but not least, there are many other problems. How we can decide whether the realization of D is connected or not. As I said, the above problem is related to the connectedness of realizations, and for a given set of integers like this, 1, 1, 2, 5, 6, something like this, how we can decide whether the realizations will be connected or disconnected. In some cases, both are possible maybe, we don't know yet. So let's see. I shall start with the fundamentals, my friends. A graph is a geometric figure. Of course, all of us probably know about what is a graph. It consists of some dots. These are called vertices. If you work with networks, they are called links, for example, or in some other area, they are called arcs. Many names according to what you are studying with these graphs or what you are applying them. So some arcs, some edges between some of the, not all of the. If all the pairs are connected, then this is a complete graph. It's also a graph. But in general, some of the vertices, vertex pairs are joined by edges. So these are 1, 2, 3, 4 examples of graphs. This is disconnected. You see 2 components are there, 1 edge and 1 larger component. This is only 1 component. This is a tree. This is a tree, but this is a 3 cyclic. The cyclomatic number, you remember, is 3. 1, 2, 3 faces. This is a unicyclic graph. So this has only one face. We shall mention about this in a minute. So graph is an easy drawing. From primary school, we have drawn a lot of graphs, I'm sure. So main idea is degree sequence. Main idea is the degree sequence. What is a degree sequence? Degree sequence is a set of non-negative integers, usually positive integers, 1 to the A1, 2 to the A2, 3 to the A3, delta to the A delta. Delta is the largest vertex degree. For example, in the figure, what is the largest integer? 4 in two places. So we write 4 to the 2. What is the smallest one? It is 1, and twice ones are there. So 1 to the 2, 2 only once. You see there is only one vertex of degree 2. So 2 to the 1. 1 is the multiplicity, not some kind of power or something, okay? And there are 2 vertices having degree 3. I assume you understand the vertex degree. This is of vertex degree 4 because it has connections with 4 other vertices in the graph, okay? This is for simple graphs, of course, this definition, because if you have looked, then the number of edges may be risky to mention, so you have to adjust your definition. So the number of lines locally meeting the number of edges locally meeting at the vertex is exactly the vertex degree. In such graphs, it's easy. For example, if the figure is given to you, if the figure is in front of you, then you can easily calculate this set. 1 to the 2, 2 to the 1, 3 to the 2, 4 to the 2. Easy. This is 2, 3, 5, 7 vertex. 7 vertex graph. You see there are 7 vertices, the sum of the multiplicities. So, this will of course give us some advantage to know this. So my friends, this is degree sequence. If graph is given, it is very easy to make this list. That is, it's very easy to obtain the degree sequence. But on the converse, on the contrary, if D is given to you and you have no figure like this, but you are asked to find all figures, all graphs out of this set, what can we do? About this, we have another definition. If D is any set of non-negative integers, any set, 1, 2, 5, 6, 10, 12, something like this, we say that a graph G, any graph, something like this too, graph G is a realization of this D if the degree sequence of G, this graph, is equal to this set. So that means if you can find a graph with these vertex degrees as these integers as vertex degrees, then this set is said to be realizable. We can realize at least one graph out of it. If there is at least one graph, believe me, there are a lot. Even with 5, 6 element sets, we have hundreds of graphs. When the number of elements in the set is 10, 15, it goes to billions. Very hard problem, very big problem, and there is no formula for general number of these. So this is called realizable, as we said. Of course, from the definition, for any realizable degree sequence, we have at least one, because realizability requires existence of at least one such graph. If set is realizable, we know that for sure there is at least one graph. But how many? For example, for this set, very small set, 5 vertices, you see 1, 4, 5. Very small vertex degrees. So we have this graph, including a triangle, and we have this graph, including a quadruple, square looking like, okay? They are not isomorphic, so they are different graphs, but they have both the same vertex set. So they both correspond to this set, this vertex degrees, this degree sequence. Are there others? The problem is that only 2 is okay, but if there are more, believe me, there are at least 5, 6 more. Actually 15, 20 more. Yeah. So we can say, what we can say is, for one set, we can have a lot of graphs, a lot of realizations. Now, the topic is omega invariant. So I shall mention now very briefly about how we invented actually this omega invariant. Actually, it goes back to 6 years ago. My PhD student was working with molecular graphs and came to me with some repeating formula. This A1, A3, 2A4, 3A5, delta minus 2A delta. He told me that this 2 is changing. Sometimes it's disappearing. Sometimes it's becoming minus 2. Sometimes it's becoming minus 6, plus 6, plus 4, plus 8, but always an even number. So, of course, this is a nice pattern. Of course, we discussed about, we searched about for which graphs it is 2, for which graphs it is 0, for which graphs it is 4, for which graphs it is minus 2. And in one of the old books, a French book by Henry Weber, it's not a well-known book, but it's a big book, this formula was there. A1 equals to A3, 2A4, 3A5. This is only valid for trees. And the number of pendant vertices, which are called naturally as leaves because of a tree, okay, the number A1 of the leaves is given by this formula. And this left-hand side up to 2 is repeating, but this number is changing for other graphs. That is, for any tree, this equation is false. The equation holds, okay, with 2. But some other graphs, for some other graphs with cycles inside, closed faces, then this 2 is changing. So this invariant part had to be defined by something, and we called it omega invariant. Since then, we have done a lot of applications. In the references, you will see some, and I will mention about some. We have applied it to algebraic graphs. We have applied it to number theoretical graphs. Fibonacci graphs, Lucas graphs, Fibonacci graphs, Pell graphs. Whenever you have an integer sequence, special numbers, integers, then you can correspond some graph by these numbers, satisfying some conditions, and the determination, the classification of these graphs is a nice problem. So we have done this. We have done combinatorial calculations we are still doing. We have done topological calculations with indices and their applications. So omega invariant is indeed combinatorically, topologically, algebraically, geometrically, in many terms, it's applied to many places. So what is omega? You will remember A1 was on the left-hand side, so it's on the right-hand side, and therefore it says -1 coefficient now. And this was 2. This was 2 on the right-hand side. Now it must be -2 if we have a 3, okay? But in general, this is changing. And this changing part is called omega invariant of G. So this is also omega invariant of D. Because D is given, you can calculate this number. It's an invariant. For all graphs out of this set, we have this number as invariant. Okay? So, actually, my friends, I will give you a clue. It is very easy to calculate. I will give examples. Omega invariant. Why? Because you just subtract 2 from each vertex degree. From each integer here, you subtract 2. If you have 1, this is why it's at the end. If we have 1, then 1 minus 2 is minus 1. Minus 1 times A1. A1 times minus 1 actually. A1 times minus 1 is here. For 2. 2 minus 2. You subtract 2, you remember. 2 minus 2 is 0. Times A2. 0 times A2 is 0. So there is no A2 as you can see in this formula. Very natural, I will explain. For 3, 3 minus 2 is 1. Here 1 is there. 1 is there, you see. Times A3. Next, 4 to the A4. 4 minus 2 is 2. 2 times A4. 3 times A5. Delta minus 2 times A delta. Okay? So, these multiplicities times the degree minus 2. That means, again, one final time I'm mentioning, you just subtract 2 from all vertex degrees and their sum will give you omega invariant. Next, we calculate 3 different examples. In the first one, the omega invariant is 2 times 1, 1 times 0, 2 times 1, 2 times minus 1, of course, the first one, 1 times 0, 2 times 1, 1 times 3, 1 times 5. You see? Usually this minus 1 is written at the end. You see? It is the only minus 1 item, so it's written at the end not to cause a complication. So in this case, this is 5, 10, minus 4, 6. Then D can be 6, for example. You remember it was an even integer. Don't forget. So in the second example, particularly chosen examples, of course, this is 1 to the 7, 2 to the 6, 5 to the 1, etc. And omega is, you start with 3, but you can start with the first one again. 7 times minus 1, it's at the end here. For 2, it's 0. You won't see anything related to these 2's here. Even if their number is 1000, doesn't matter. It does not affect anything. Geometrically, it has a meaning. It's about the number of cycles, so we will see. The next one, 3. So 2 times 3 minus 2. 2 times 1. 1 times 2 and 1 times 3, you see. Then we get 0. That means omega invariant sometimes can be 0. It was 6 in the previous example. Now it can be 0. And in the next one, it can be minus 2, minus 4, we see. So again, very quickly, I will do calculations. 13 times 1 minus 2, minus 1. And 2 times 1, the first term. 1 times 4, the second term. 1 times 5. Okay? So we get minus 2. So my friends, this number so far seems to be an even integer. 0, minus, positive, doesn't matter. 0, negative, positive, but it's an even number. Is it always so? So this is properties. Omega invariant has very nice properties. You remember the long formula? Sometimes if you have the number of vertices and edges, you don't need to calculate all these formulas. This is an alternative formula for omega invariant. It is very easy conclusion of some fundamental sums related to graphs, of course, like handshaking lemma and the number of edges. These formulas come together to give this formula. Omega is equal to twice the number of edges minus the number of vertices. Okay, so these are integers. Twice an integer is an even integer. So omega must be an even integer. Okay. Of course, for a given number of vertices, we know the interval of the edges, the number of edges. Okay. For example, for 6 vertex graphs, we know that how many edges we can have in different cases. Okay, maximum the complete graph 6 times 5, 15 you will have. Between 0 and 15, any number we can have as m if n is 6, for example. So you can calculate all these numbers that omega can take. So it's an even number. Let's remember this. This is a very big paper actually in this page I'm mentioning, fundamental realizations. We formed 3 families for all graphs, for all planar graphs, of course. For planar graphs, we have defined 3 conditions. One central condition is omega equals to -2. So all graphs, all degree sequences with omega equals to -2 forms a large infinite class in the middle. Omega, you remember it's an even number, greater than or equal to 0, and omega is less than or equal to -4 are 2 endless groups, 2 endless families. So we have 3 families of infinitely many graphs containing each of them containing infinitely many graphs. So what is the difference between these 3? All the results actually are stated and proven in these 3 cases differently. So for example, if omega is equal to -2, we know a lot of things. If connected, for example, it must be 3 as in theorem 3 says, okay? The necessary and sufficient condition for a simple connected planar graph is a 3. This condition is the sufficient necessary condition is omega equals to -2. If you have a connected simple planar graph, and if you want it to be a 3, then this is a new condition for being a 3. You know, there are lots of conditions for being a 3 for a graph. So it is omega equals to -2. Omega equals to -2 and connected, then that means this is a planar graph and it's a 3. Okay. Of course, for other 2 classes, we have similar algorithms, similar results, similar theorems, similar theories. So my friends, this is another important application of omega invariant. The number of phases, the cyclomatic number actually in graph theoretical terms, is given by r equals to omega divided by 2 plus a number c. The number c is the number of components. We mentioned before, you remember, the number of components, the number of connected subgraphs of the main graph, G. So, if you want to find how many faces your graph will have for a given set of D, okay, then you calculate this number and they must give you how many components they want. So, if they don't give, then you will have to know the minimum number of components and the maximum number of components. In the next slides, we shall see this. So remember, the number of faces is half omega plus the number of components. For example, if you want connected graphs, connected realizations of these integers, then C is 1. But if you want 3 components, then C is 3. The number of faces will also increase by the number of components. Now, my friends, some problems, and we are going towards the end of talk. Is the set realizable? What is the cyclomatic number, the number of independent cycles of any connected realizations? So, this set is a big one, 3, 4, 7, 10, 12 vertices. You see the sum of the numbers in brackets, 12. So, 12 vertices can be ordered in many different ways. If this is realizable, which is realizable, we will see. So, in how many ways we can draw these graphs, we don't still know. Soon we shall know, believe me. But at the moment, we don't know the number of realizations. But what about the cyclomatic number? We know about this. And it asks you connected realizations. Let's see. This is this set, you remember, the same set. I just copied it here. Omega is 14. You can calculate if you want 3 times 1, 3 times 2, 1 times 3, 1 times 5, minus 3 times 1. Okay? So, this is 14. It is even, and if it is even, you remember, omega must be even, so it is an omega number, so it is realizable. Also, by corollary, the number R, you remember, so it was half omega plus the number of components. So, as it says connected, C is 1, omega is 14, so the number is 7 plus 1 is 8. So, probably 10,000 graphs you will draw, and all of them, all the connected ones amongst these will have 8 faces. If 7 and connected, then it's not corresponding to this. If 9, it's not corresponding to this. Okay? Exactly 8 faces due to omega invariant. The second problem, my friends, the maximum and minimum number of components. Above we mentioned about we shall need this because to find the number of faces are what we need to know the number C. The number C is changing, and if some number, some parameter is changing, then you have to know either the formula or lower and upper bounds. Okay? If you don't know the exact numbers, like in Diophantine studies, for example, they always make lower and upper bound and they study in this region because it's a big calculation with these equations. This is something like this. We have to know minimum and maximum number of components, connected components. Okay? So, this is the set. 9, 11, 12, 13 vertices. 13 vertices. Most of them are pendant vertices of degree 1. Okay? Let's see. For this minimum and maximum number of components, we have given 2 formulas. In 2019, my student and I gave the following useful result. If D is this set, the classical one, it's a realizable degree sequence. Otherwise, no need to talk about it because there is nothing out of it, no graph. Here, realizability makes sense. We have at least one graph. And if we have one, we know now at least thousands of them because it's a big set, it looks like. The maximum number of components, the maximum number, you remember 2 numbers we are looking for. The maximum number of components is the sum of AIs, the sum of multiplicities of even vertex degrees, A2 plus A4 plus A6 plus A8 up to the final even index, okay? And half time the same sum for odd vertex degrees, okay? A1 plus A3 plus A5 plus A7 plus up to the last one. A delta either belongs to the first group or the second group, okay? So up to the last one, we calculate this. Why we multiply by a half? This is due to the handshaking lemma, okay? One odd vertex cannot form a graph. This is the idea. We need at least two odd degree vertices together in the same component to make okay, I'm finishing very soon. The maximum number of components. Yeah, this is the number. And so we have 7. And this is maximum number of components. So, my friends, the second one, this is C min. C minimum is the maximum of 1 and minus omega a half. So, my friends, this is also, which is 1, of course, 1 means as omega equals to minus 2, you remember, it's a 3. So, and the final problem is about the realization and connectedness. How we can decide? So, my friends, the result I will give you and finish. Omega is less than or equal to minus 4 means all graphs are disconnected. If omega is greater than or equal to minus 2, on the contrary, then the graph is both possibly potentially connected, it is said. Some of them are connected, some of them are disconnected. So this is a very strong formula, strong result for connectedness of graphs. So there are lots of references. Of course, this is the definition of it. Extremal problems, this one was. Graphs and cyclicness. This is existence of, this is Edmonds' term, I didn't mention about it. This is Havel-Hakimi process I mentioned about realizability. This is for matching number by means of omega. This is connectedness by means of omega. This is nullity by means of omega, cyclomatic number. This is topological graph indices. We can calculate the extremal values of them by means of omega. This is cyclicness by means of omega. This is independence number of graphs and line graphs of trees by means of omega. You see every idea, almost every idea in graph theory, any parameter can be related to omega invariant because it's a combinatorial formula and it gives you some, at least some bounds, if not exact formulas. So thank you for listening. I think I passed my time a little bit. Thank you very much for listening.
Okay, thank you very much to Professor Ismail Naci Canggul for the interesting and insightful presentation. Okay, now we begin the Q&A session. For those here in person, please raise your hand. For online participants, you can type your question in the chat box or use the raise hand icon and unmute the microphone. Okay, anyone to ask the question?
Thank you, Professor Kangal, giving a wonderful talk. We are happy.
Professor Jangil, thank you very much. Very nice talk.
Thank you very much, Professor Simsek.
They are here.
Just a minute.
Hi, Professor. We are here, Professor.
I can see you. And Lokesha.
Yes.
And Venkat.
Yeah. See you
I
sometime.
can see you while you are sitting. Don't stand up.
Okay.
Good to see you all.
Very wonderful.
Thank you. Best regards.
Yes, yes. check already there.
Okay, thank you very much to Professor Ismail Naci Canggul, and please give applause to Professor Ismail Naci Canggul. Okay, for the next keynote speaker are presented by Professor Yilma Simsek and moderated. Oh, yeah. Okay. Ladies and gentlemen, before we entering our next presentation, we will appreciate the keynote speaker by giving him certificate symbolically to Professor Ismail Naci Canggul. Thank you very much to Professor Ismail Naci Canggul for the fantastic presentation. This is your certificate as the keynote speaker.
Thank you very much. It looks very colorful, like Indonesia and Indonesian people. Thank you very much.
It's so colorful. Okay, thank you very much to Professor Ismail Naci Canggul. Okay, for the next presentation will be chaired by another moderator. So I will give the stage to her. Okay, thank you very much.
Assalamualaikum warahmatullahi wabarakatuh. Om Swastiastu, salam kebajikan dan salam sejahtera untuk kita semua. Good afternoon, ladies and gentlemen. My name is Syabana Nurin Nadia Aziz, SPD, MPD, and I will be your moderator for this plenary session. I hope you had a refreshing lunch break and now ready to continue with our conference. Before the presentation begins, let me inform how the presentation will be going on. The keynote speaker will be invited to present to the material about maximum 40 minutes. Let us now begin for the first speaker. Our speaker is Professor Dr. Yilma Simsek from Akdeniz University Research Information System Turkey. Professor Dr. Yilma Simsek completed his undergraduate, master and doctoral studies at Çukurova University, Adana, Turkey, focusing on polynomials and special numbers since 2005. He has been teaching at Akdeniz University after previously serving at Çukurova University and Mersin University. His research interests include applied and pure mathematics, particularly group theory, graph theory, geometry, and mathematical analysis. Professor Yilma Simsek, the time is yours.
Yes, thank you very much for your introduction about me. Before me, Professor Cangül give very nice talk about graph theory. Today, I give you some theoretical construction of sextet polynomials in chemistry with the aid of these genetic functions. These genetic functions recently constructed by me. My aim is to construct general ordinary generating functions are including Fibonacci polynomials, Lucas polynomials, Chebyshev polynomials, Humbert polynomials. I think all of them are including in this type polynomials, in these genetic functions. If we read these genetic functions carefully, here Pjxj gives us the polynomials of degree G. If you take special cases of these polynomials, such as if P1 is equal minus x, P2 is equal minus 1, and G is equal to, you obtain generating functions of Fibonacci polynomials. If you take P1 is x square, P2 is x square minus x minus 1, you give genetic functions of sextet polynomials in graph theory. Now I explain the motivation and motivation of this talk about on these both generating functions. Here, Qj also is a polynomials. Now I firstly define and explain my notations. These Pxm notations is meanings P1x1, P2x2, Pmxm. Then you have a m variable polynomials in order to give all ordinary genetic functions of polynomials and graph and others and numbers also, special numbers. Everyone familiar with definition of polynomials? This is a definition of Pj, Xj and Qr, Xr polynomials. Every time J less than M and greater than equal 1. R is also same because we have degree of the polynomials here is C, degree of polynomials here is D. And D and C is any non-negative integers. These polynomials are closely related to Fibonacci type numbers and polynomials, Chebyshev type, Humbert type, and other graph polynomials. This chapter recently published in Springer book chapter. Today I give you. Originally, the result of this paper are published in Revista Mathematics in Springer Journal. Theorem 1. What is the explicit formula of the polynomials yn Pxm? We have a many complicated formula for these polynomials in order to compute these polynomials by using there are two methods to prove this theorem. The first proof is depend on induction, mathematical induction method. The second one is to use generating functions method and with the aid of hypergeometric functions and others. The others depend on series calculations. There are many methods to prove this theorem 1. Here I do not interested on the theorem because the proof are given in my paper, in this paper, in theorem 1. But if you know this definition, you calculate all Fibonacci polynomials, Fibonacci numbers, Lucas numbers, sextet polynomials, and Chinese and rank polynomials. Every graph polynomials can be computed by this formula. If the big problem is to understand and use this notation. This is a very big problem because if you understand the meaning of these all terms, then really it is easy to compute many nice and interesting application. The other polynomials is Sn. The Sn computed Lucas type polynomials, Humbert type polynomials, and higher order polynomials. So these polynomials given in terms of yn polynomials. Then this is a linear combination of yn polynomials. I give one example to you. Because of the time, I skipped the Bernoulli numbers. Everybody familiar with the Bernoulli, Euler, Genocci numbers. Now I give indices, all indices, higher order Bernoulli polynomials. Pmxm, B1, the order of the B1 is V1 is the degree of the Bernoulli polynomials, the second order, third, and m. We have a m indices here given by the Bernoulli polynomials. Here, if you look at here, k every time less than m, then if we use the generating functions, substituting these indices in the generating functions, our generating functions is given like this. These are rational functions. Then this is also meromorphic functions because depend on the pole of the Bj xj. Then if m equal 1 and k equals 0, we have a two variable. Look at here, we have two variable, b1 and b0. If I compute yn, bx is give the first degree of the Bernoulli polynomials of order n, the power of n. If you compute these polynomials, you compute yn polynomials. Is here n is the power of the polynomials here. Then if you compute Sn linear combination of yn by the b0 times minus b1 over the power of n. Then after these calculations, I give general formula for Bernoulli numbers. For instance, first Bernoulli polynomials, the degree of 1, x minus 1 over 2. The second degree of Bernoulli polynomials, x square minus x over plus 1 over 6, and that continue like this. This is for Pm, xm. For Qm, we have 1, x minus 1 over 2. Then this also is Bernoulli polynomials. By using this computation, the for first b0 1 is x is 1, and b1 is x minus 1 over 2. Then if we compute Sn given like this. Sn is also because this is a linear combination of yn is b0 is 1. Then we obtain this nice formula. Then for Bernoulli numbers, I give another example to you. If m equal 2, this is a general, if m equal 2, we have this formula. This, if you look at it, this is integer part of the n over 2. If n is odd, then you give integer part. Then yn, the indices b1 and b2 is a Bernoulli polynomials. We obtain this very nice formula. In my aim to give the graph polynomials. This is also any other graph polynomials. I do not know what is the application of this. This other researchers, other applied mathematicians look interested on this formula. Maybe they find another application in chemistry, in biology, in mathematics and other graphs. Look at this is very nice formula for Sn. Here we have a b1, b2, b0, b1. Our index is given by using linear combination of this Sn with the yn. We obtain this formula. If m equals 6, then we have a many complicated. For k equal 3, we have a many complicated formula. Here, if k equal 3, we have a stop t power 3. For m equals 6, we stop with t power 6. Then we have b1, b2, b3, b4, b5, b6 degree of Bernoulli polynomials on the denominator. In the other side, b0, b1, b2, b6 other Bernoulli polynomials. After some easily calculation by using theorem 1, then the Sn is a linear combination of yn is given like this. This is a yn. If I take linear combination of these polynomials with the help of yn, the Sn is given by this formula. Really, this is a very complicated formula if you look at this formula. Very, very complicated. If I give another special case of this formula, all xj is equal 0, yg is equals G plus 1. Then I give some number theoretical example now. We have this genetic function, B1, B2, this order of the Bernoulli numbers here, B01, B12, BK, K plus 1. By using definition of the higher order Bernoulli numbers, we get these factorial numbers. By these Sn also reduced to this closed form, and Pxn gives us very nice formula, -1, 1. If you give these formulas, then we obtain Yn is given these factorial numbers like this. Then if I use our first theorem, if I computed P1 x1 is minus 1, then by using these factorial numbers, Yn easily computed like this. There is no polynomials here. You obtain another special polynomial numbers with the aid of the special case of Bernoulli numbers. For instance, these sequences, Yn sequences, depend on factorial numbers given like this. There are many applications of these numbers in graph theory. With the aid of the OIS library, you find maybe in future I added this in OIS sequences for this polynomials. This is the first definition given by my book chapter. Yes, as for S1, this is a linear combination of Yn. We obtain this theorem. These are factorial numbers also. These numbers are given like this by this table. You find all S1 is depend on factorial numbers. Then if I take another application by the table, we have this very complicated table here. It is possible give many open question. If anyone solve this question, really they obtain very high quality papers in Journal of Number Theory like this, because there are very difficult questions. How can we give the genetic functions for these numbers, for these polynomials? Really, this is another dimension of the studies of this talk. There are other open questions given here. Maybe I give some example to you for Fibonacci numbers. If I take P1, x is minus x, P2 is minus 2, Q1 is 0, Q2 is 1, we obtain genetic functions of the Fibonacci numbers. These are genetic functions of Fibonacci numbers. Fibonacci numbers can be computed by the Sn. In the Sn polynomials, our first vectors given -1, -1, and the second vector is 0 and 1. If you make some easily calculation in the genetic functions of the equation 1, then Fibonacci numbers can be obtained. These numbers can be given in Cauchy books, and also Fibonacci polynomials given like this. So my generalizations is given first generalization of Fibonacci numbers, and the second example. Also Fibonacci numbers can be given by the Yn polynomials like this, and given like this. This is a closed form of the Fibonacci numbers. All can be given by my theorem 1. Theorem 1 give every formulas for Fibonacci numbers, Fibonacci polynomials, all of them. And if you look at here, this is a Lucas polynomial. If I take first vector minus x minus 1, and second vector is 2 minus x, we obtain genetic functions of Lucas polynomials like this. These are genetic functions of Lucas polynomials given in special case of these two polynomials. After some easy calculations, it is easy to give computational formula for the Lucas polynomials different from the other usual formula. This is a general formula for the Lucas polynomials. I give all my formula is not depend on known formulas. This all of them is new. Yes. Now I give Lucas polynomials, another form of the Lucas polynomials by using Sn and Yn polynomials. We have a two polynomials 1, 2, 3. I give 3 formula for the Lucas polynomials like this. Also the I give another polynomials is 4. Now it is time to give you PAL polynomials. Look at PAL polynomials is also very important in the graph theory. PAL polynomials is also depend on Sn. If vector 1 is minus 2 minus 1, second vector 0 1, then you have a PAL numbers. For PAL polynomials, if you change the vectors 1 minus 2x and minus 1, the second is 0 and 1, you obtain PAL numbers and polynomials by using Y and by using Sn. Yes, by using Sn, the PAL polynomials are given by this closed form. This is really, if you look at the literature, all formula given by the recurrence relations. It is very difficult to use the recurrence relation to compute all numbers. But my formula directly, you give them, if you give any algorithm in the computer, you easily obtain all of them. But by using the recurrence relations, in the computer science, you use many times. Then other PAL polynomials given like this. The other PAL polynomials, I give 10 times 10 different formula for PAL polynomials. Yes, now it is time to give some graph theory applications. These anti-chain polynomials given by these genetic functions. If I give my vectors minus 1 minus x, the first indices, the second minus x, the second vector 1 and x. If I use in the genetic functions of Sn, we obtain these rational functions. By using this rational function, you obtain anti-chain polynomials genetic functions. Then these polynomials can be easily obtained by the Sn polynomials. What is the meaning of Sn? If you give some computation anti-chain polynomials given like this. This is a computation of anti-chain polynomials in graph theory. I say here this is a presumably new computation. Maybe other modification of this formula can be given in the literature, but I do not find. So I writing these sentences. Yes, the beta polynomials is also important in all branches of science. This can be computed by this in terms of the anti-chain polynomials. The anti-chain polynomials is also depend on beta linear combination of beta polynomials. And maybe I skip this. Beta polynomials, I like these polynomials very much, but here I have no time to give you. Now I give classification of my polynomials. If you take Pxm, if your vector minus 1, Q vector is 0, 1, you have a Fibonacci numbers. And x minus 1, the first vector, second vector 0, 1, you have a Fibonacci polynomials. Minus 1, 2 minus 1, Lucas polynomials, minus x minus 1, 2 minus x is Lucas polynomials. For this, you have a PAL polynomials, PAL numbers, PAL polynomials, and Pell-Lucas polynomials, Pell-Lucas numbers, anti-chain polynomials, Jacobson polynomials, Jacobson-Lucas polynomials, Vieta polynomials, all of them given in this site. So my genetic functions really give you all computational of the known and unknown formulas. Now it is time to give another application of Fibonacci and J-gonal and trigonal numbers. So we have a for Fibonacci we have a in 3-dimensional. Then our vector is on 3-dimensional. We give you Fibonacci, Lucas, and other polynomials. If you change dimension, you obtain another kind of polynomials. Now we are in the if your dimension is 4, you have a hexagonal prism number and other numbers like this. -4, 6, -4, 1. And the first vector, the second vector is 0, 1, 10, 7. You have a hexagonal prism number like this. If you give another dimension, if you change dimension, you have another kind of polynomials. Now, sextet polynomials is these two Chinese mathematicians or chemistry. They are study on hexagonal system of the graph theory, or in the chemistry. They study on the sextet polynomials due to this polynomials. Maybe I generalize this form. The sextet polynomials really depend on my polynomials like this. These are the genetic functions of sextet polynomials. You have a two variable here, Your first indices -x squared, -4x, and -1, and the second is x squared. But if you substituting in the theorem 1, you obtain the genetic functions of sextet polynomials. Sextet polynomials can be used in calculus structure in benzoid, hydrocarbons, and other areas, and aromatic hydrocarbons. I do not study on these tails and their applications, but there are many papers and many works on the sextet polynomials. This hexagonal system, since they are symmetric and unimodular, and low concave, and also there are many asymptotic applications of these numbers and polynomials and genetic functions. So the interested listener read my paper and Lee paper in deeply. There are many applications on these polynomials. Now it is time to give a closed form or explicit form for sextet polynomials. I have before mentioned these are very application in the graph theory. If you look at here, this is really you have a two formula for sextet polynomials. By using this and this, it is easy to compute all sextet polynomials via the polynomials Vn. It is this paper, this talk involving many interesting generalization of the polynomials and numbers, and also in other applications. So I focus on this. This is a analytic properties of sextet polynomials given in journal Mathematical Chemistry. Now I generalize these sextet polynomials, and others I generalize my first two variable and Humbert type papers. I also generated both these genetic functions, and also all my generalization all my generalization given by this paper. If I find, then I divide it with you. Yes, in this paper, you find all application and closed form of the sextet polynomials and general form of the ordinary genetic functions, and given the many known and unknown formulas depend on graph polynomials. Thank you very much for your patience. You listened me.
Thank you very much, Professor Yilmaz Simsek, for the interesting presentations. Now we begin the question and answer session. For online participants, you can type your question in the chat box. For those here in person, please raise your hand.
Abdulmecid Bayat, maybe ask a question.
Yeah. Any question from some participants? Yes, Professor.
Yes.
Your slide presentation is very wonderful.
Yes, you are welcome.
So we are now in Bali. Last 2 days in Jember. Actually, I hope that
I want to there, but it is impossible now. Yes, maybe next time.
hopefully next time, next year, yeah.
Yes, yes.
Professor, yes.
Professor Bayat, hello.
Professor Bayat, yeah. Okay,
Please you open the Professor Bayat.
Yeah, Professor
Yes,
Bayat.
I do not hear him.
Hello, how are you?
Hello, how are you, Professor Bayat?
Good, thank you.
Oh, it is nice
How
to
are you,
find you.
Professor Duffy?
I'm good.
Professor Tafik is very good now.
Yes,
He's very happy.
Sorry
Where
about
is the Professor Lokesh?
Professor is just somewhere here, having got, I believe.
Okay.
Okay.
Okay, bye. Have a nice day.
Bye.
Hello.
Hello, Professor
Professor.
Lokesh. How are you?
Fine. Thank you. We missed you here this time.
Yes, we
Maybe
also
next
miss you.
time.
Yeah. Due to you and Tefik, I give this talk.
Yeah. Thank you.
Have a
Thank you
nice
very
day.
much. Thank you very much,
Okay.
Professor.
Okay, bye.
Bye.
Professor Bayat, hello.
I have one question, but maybe time that's not possible to. Just Professor Shemshek, did you consider the transform milling for your generating function and so on? Maybe
Maybe with you.
you obtain some. You go to another
Yes.
word for L
Yes.
function and
There are
special
many
value.
applications of the Mellin transformation and others, integral transform. Yes.
Yes.
Okay,
Yeah,
thank
very
you.
interesting. Yeah. Okay.
Yes, thank you very much.
Thank you.
Yeah, thank you. Yes.
Thank you very much. Give applause for Professor Yilmaz Simsek. Ladies and gentlemen, before we entering our next presentation, we will appreciate the keynote speaker by giving him certificate symbolically to Professor Yilmaz Simsek. Thank you very much to Professor Yilmaz Simsek for the fantastic presentation. This is your certificate as the keynote speaker.
Yes, I take picture. I take picture.
You, Professor, we will send you. No problem.
No, for Professor Bayat picture.
Take please again. 5 or 6.
Thank you very much.
Yeah, okay.
Now we continue to our next presentations. Our next speaker is Professor Abdelmajid Bayat from Université de Val-de-Sors, France. Professor Abdelmajid Bayat is a number theory at Department of Mathematics, Université de Val-de-Sors, whose work beats algebraic and or analytic number theory, modular forms, special function, and etc. He earned his PhD from University Bordeaux and has supervised doctoral students in Paris-Saclay and partner institutions. He maintains an active international collaboration network and extensive publication report. Professor Bayat, the time is yours.
Just let me, where is my, just open my, okay. Okay, let me open my file. And I will share with you. Yes. Okay, thank you, Professor Dafiq. Thank you, Professor Lokesha. Thank you all. Thanks for all the organizing organizing committee to give me this opportunity to share with you my work on the Eisenstein series and Dedekind eta function. So I prefer to be face to face, but this time it's very difficult to be face to face. Yes, today I will focus on two type of some series, U and V, and which called the Eisenstein series associate to character. Character key is the some special character. In general, instead Legendre sample, we can consider any directly character. So I will, in next slide, we will see what is Legendre sample modulo prime P. So anyway, in this talk, I want to focus on this series and the other two series. Both of them are called Eisenstein series. This is, as you say, Q series. Q series. Q is exponential to PA2, where 2 is complex with imaginary part strictly done greater than 0. And here is the L function, the directly function associated to character Q. It's well known for person. This is a series so associated to Q. And what we know for the expert is this kind of series are modular forms of weight. If you fix the R here and prime P here, you obtain Eisenstein series give a concrete example of modular forms of white R, and for respected to groups, this group, what we call it, congruence groups, gamma 0p, and associated to character Q. So the problem in the 19th century was how to construct a modular form for fixed white and for respect to some groups. And Eisenstein, it was the first to give some concrete examples. So what is Legendre samples, as I tell you before, are some special character. And they are very, very simple and elementary. If you consider modulo P and the Legendre sample can't, if your prime divide A or not, or if P divide A, you have 0. The values of this character is 0. And if you consider the equation x squared equal to A modulo P, if you have solution, the values of this character is 1. If not, is -1. This is what we call it Legendre sample, and it satisfies property of character. What it means, this is if you consider this kind of application from Z to 0 plus -1, it does not depend to element of Z, but it depends of them modulo P, as is written here. A over P and B over P are the same if they are congruent modulo P. So does not depend to the representative of element, but it depends to the modulo P. And this property, it says that you have some character like this. It means that you have some morphism from this group to these other groups. So it's very nice, and Legend can compute them in general, and E over P is the power P minus 1 over 2 of A modulo P. So let us give you a concrete example. The problem in the beginning is to study the Eisenstein series. There are two kinds of U and V. And the problem, you have Q series in left side here. And we want to study their propriety, arithmetic propriety. And Ramanuja was interested with this, and he succeeded to transform these Q series to a product, infinite product, using the Dedekind eta functions. So without proof. Later, Bailey and others can prove this. So here you have concrete example. If you take prime P is 5, and you consider the directly character associated to that prime, and you obtain here. Let us return. Yeah. So here we give the example R equal to 2 and P is 5, and what happened with those kind of series. So Ramanuja was interested by this, and he conjectured that this Eisenstein series is exactly quotient of eta function involving 5 here and 5 here. And for other one, for view is eta function, but you twist 5 here. And at that time he does not prove anything, but later Bailey proved the first one, and Bailey, Kolber, and Mordell, they proved the second one by different method. And later we will see that there are behind this many theories, there are machinery to prove such kind of identity. So I give you a new one. If you take R equal to 6, for example, and you take also P equal 5, you can obtain. There is a new one. This one is proved recently by Kolber. But the second one, I don't find it in the literature. This is related to the second Eisenstein series, V. This is U, this is V. I cannot find it in the literature, but I prove it. So you have this kind. So you can, the philosophy behind that, you can change the white air, and if you fix the prime 5, you can produce many identities relating Eisenstein series associated to Legendre character, and in the left side the Q series, and the right side you obtain infinite product in terms of eta Dedekind function. What is this? Oh man, I don't know. Okay. What is this? Oh, you see my slide or not? Moment. There's some problem. Okay. Sorry. Okay. Let us continue. Now I give you other example. If you take the white is 3 and the level is 7, you obtain a new kind of identities. So you have here the Eisenstein series U, and you have modular equation in the right side using eta function here related to 7. And also you have identity related to the second Eisenstein series. Those kind of two identities are proved by Finn. So now I will give you a new one, really recently proved by me and my student. If you take R equal to 9 and you P equal to 7, you have many identities. As you see in the left, you have all times Eisenstein series, and in the right side using polynomial and eta functions. So here you, okay, let us see. And you have other example for R occur to 6, and for level 13, you have also others formula. And for P, you can change the white. And now I want to, as I share you with some examples, I want to focus what is the strategy and what is the problem and the toll behind this. As you see, firstly, you have some key series like Eisenstein series or modular form or Kesp form. You have in the additive word. And the right side, we want to write them in terms of infinite product to like eta function or eta quotient. Yeah, we give to multiplicative words. And the problem is how to do this, how to connect this. As I show you in examples, you have some modular equation. We obtain in Ramanujan, others. And I will tell you how to obtain it, because the toll how to obtain it, I will tell you after that. And after that, when we obtain the modular equation, what is the interpretation behind this? If we look at the coefficient in our modular equation, we have some congruence, Ramanujan congruence can be obtained directly from that modular equation. And this is the word of partition functions. And I tell you briefly what is the toll behind the links, how to obtain all these links. Yeah, this is behind this is modular forms and eta function. First, we in left side you have Eisenstein series, and we prove that there are some modular forms. And when we have modular forms, by Newman methods, we can construct, we can write them in terms of quotient of eta function. This is first step to Newman gives a method, and he can see check after some check and condition to check, and you can write or not. If you can write it, yeah, you use some others method to efficient method by Sturm. I will show you in the next slide. And the Sturm method is based on, you must construct some basis from the modular forms on of level L and associate to character of directly character. And you must pick some basis there, and not any basis, but some what we call it good basis as Milner basis or others. And there are some algorithm using Maple, and some software. We can obtain all these bases for modular form of weight key and for fixed subgroups. And the problem is very difficult if you change the level. There are the level is very difficult. It depends because the geometry of the modular curve. If the Janus is zero, is very is not. Yeah, every tank is known in the Janus zero because there are some algebraic geometric result due to Ligoza, and it gives you the Janus of modular curve, and it gives you what the theory of the space of modular form for a level n and associated to character q. Let us move. I give you one example, a basic example in the literature. Here I for that method for how it's very powerful this method. I give you, for example, if you take n, the basic one is if the number n is 1, and the number if is 1, you have the congruence group is the modular group here. The group is for the first level n equal to 1, your modular group is SL2. And there is the theory of modular form is very beautiful. It tells you that every modular form in SL2 may be expressed as rational function in eta function. This combination eta z, eta 2z, and eta 4z. And how to prove it? It's very known that modular form, any modular form on SL2Z is rational, is expressed in term Eisenstein series E4 and E6. The classical one, the character here, there are no character here. The character is trivial, is very simple one. Eisenstein construct that kind of series, and the theory of modular forms says that any modular forms can be expressed as polynomials, rational function, as rational function in O4 and E6. And now we can prove that if you want to express any modular form in terms of eta 2z, and eta 4z, it's sufficient to give the O4 and O6, what in terms of eta. And I give you this. So the answer is this. By the Eisenstein series of white 4 and white 6 are expressed like this, and the proof is very simple, as you see, because in the philosophy of modular form, you say this is modular forms of white of white 4 for SL2Z, and you must combine, you must construct another modular form using eta function, and this is obtained by Newman construction gives you this kind of right side. This is if you check by the propriety transformation formula of eta, you can show this also modular form on SL2Z has same weight of this one. So if you have two modular form an SL2Z with same weight, just by Sturm, there are another method by Sturm result, check only the first coefficient of Fourier, and if they have the first coefficient are same, your modular form are the same. That's what I see here. First, we observe that linear combination of eta function on the right hand side are modular form of weight 6 and 4 and 6 respectively on the group gamma 04 with character, some character. But if you make 16, you have exactly modular form of weight form of gamma 0. And the identity are same because the first few coefficients of Fourier are same. This is a powerful method of modular form. So, and we can do that for high level, but it's more difficult because in SL to Z, we check only one or two coefficients, the first two coefficients of Fourier series. But if your level is high, you must go for more and more. And there are some band how you must check, and it depends to the are given that band are given by Sturm method. So, and now let me recall something on partition theory, motivation, and I want to connect what I tell you before with partition theory. So, as you know, a partition of number n, it's a finite increasing sequence of positive integer lambda 1, lambda 2, lambda r. How many way to write n in this way? How many way to write n like increasing series like this? For example, 5, if you take n equal to 5, you can write it 5, 4 plus 1, 3 plus 2, 3 plus 1, 1. Only you consider only decreasing sequence, and you have here a result for 5. Okay, and as Professor Shemshik said before, there are to compute all these values. You have good powerful method. This is the generating function. You consider the generating function of those objects Pn, and you have infinite product, and is exactly eta function. The generating function of partition of number here is Q1 over 24 over eta Dedekind function. So there are extremely, the partition theory are extremely connected to eta Dedekind function. And the problem is how to compute those values. And Euler was also interested by that and he gives a recurrence formula, like in the talk of Professor Shemshek. This is if you want to obtain efficient or algorithm, you must look for the recurrence things. This is the recurrence formula, how to obtain the values of the partition. And later McMahon he used this recurrence without computer. In I think in 1911 he compute for he give list for all number up to 200, but it's very difficult without computer. But he succeeded. I give you here, share you with you a list of P1. From P1 is equal exactly 1, and P2 is 2, and 3 is 3, and 4 is 5. Using only this recurrence formula. But I don't give you the values of 200. Very high. But at that time, McMahon he succeeded to use this recurrence formula and give the explicit value for all these numbers between 1 and 200. So talking on the partition theory, are most of powerful result is related to Ramanujan congruence, because here Ramanuja, I don't know, he succeeded to conjecture that. He look at the first values of P1 and to make be 20, and he conjecture this conjecture. I don't know he can obtain like this. He conjecture, you consider the sequence of 5 power g n plus 1 here, Yeah, this is obtained here. Yeah, he consider this sequence and this sequence and this sequence in the partition function, and he note that all these values of this partition function are divided by 5 to g. And for this sequence, the arithmetic one, the values of p, there are factor 7 power this one. And if he consider this, all these values are divided by 11 to g, and no other one. If you consider another prime, maybe 13 or 17 or 29 or other one, there are no such kind of congruence. So, and in 1919 he conjectured that he proves only for g equal to 1 here. For this first one, here he for this one, and he does not prove the others one. But later Watson and others, Atkin and Hershon and many others, they prove that conjecture, and he correct some terms, but his conjecture still correct. So, but there are many. The theory at that time is Q series, a generating function, and the Jacobi forms and the Euler's recurrence formula. And modular theory, modular machinery comes later. And now we can instead of those kind of congruence, we can relax and can give more others congruence. And if we want to do that, we can maybe relax, look at only on the eta quotient. So I make some variation of eta. Here I consider some eta function like this with parameter lambda 0, lambda 1. I wrote it, we can write it as infinite product. And as I tell you before, let me check here, let me show you. Yeah, as I tell you here, the generating function of partition function is eta function, 1 over eta. So instead of 1 of eta, we can consider maybe 2 eta or many, and we can expand them like a series, and we look at the generated the coefficient of the generating function here. So I come from now. Ramanuja come from the partition and go to eta function. Now I want to come back by using more flexible object here. So my idea is like this. I take any quotient of eta function, and we can write it as infinite product, and we can look at the key series associated to this one, and we obtain some new coefficient here, and very interesting coefficient. And for example, if you take lambda 0 equal to 1 and lambda 1 equal to 0, you return directly to Ramanuja. But here we have many parameters, many variations. So, and we obtain similar if you for any lambda 0, lambda 1, we obtain same result as Ramanuja. So look at here. If you take L5, 7, 11, 13, 17, and with this kind of generalization, we can involve many other prime, not only 5, 7, and 11 like Ramanuja, but we can involve more. And we have similar result here. So for this kind of partition here, function, if you look at the values of that term, the coefficient here, at this arithmetic function here, arithmetic and sequence, the values of our partition function are divided by L power to ER. Yes, this is a paper published in 2023, and you have his reference, and you can, if you want to have more details, you can look at it and study. No, just to fix the idea, I went to give some example using lambda 0 for some special lambda 0 and lambda 1, and what is it? I will give you what is the partition function associated here, okay? So to fix the idea, because it's very, very general and very abstract, so I want to give you lambda 0 for some special example, and what is the partition function, and who study this kind of theorem in that case. So here, yeah, look at here. If you took at lambda 0 equal to 1 and lambda 1 is 0, this is the first one. You obtain exactly the generated function of partition function, and you have this, and you can use our theorem to obtain the Ramanujan congruence, the classical one. So now if you take lambda 0 equal to r and lambda 1 equal to 0, you obtain Atkin partition function, and the element here, the partition in the literature, their name are air-colored partition, and they are associated to the power of eta function here. And now if you take lambda 0 equal to 1 and lambda 1 equal minus 1, you have this kind of modular form, and this is associated what we call it L-regular partition function. And this is many mathematicians are working in this only on this partition function L-regular. And also there are L-core partition. It comes from if you specify lambda 0 to 1 and lambda 1 equal to minus L, L is the prime L. It's associated to these modular forms. And the coefficient here, what we call it L-core partition. Okay, now let me return to first example due to Ramanujan and proved by Kolber and others. This is it's come exactly what we is exactly you can get this kind of if you return from our result, if you specify to lambda 1 equal minus 5 and lambda 0 equal to 1 and prime equal to 5, you obtain this result. So this result is very powerful, and you many variation, you obtain all these kind of modular equations. Okay, and yes, and this is and you if you split, if you use this Q series of eta function, as I tell you before, because before for lambda 1 equal to 1.5 and lambda 0 this right side, it corresponds some partition function here, and the left side you have the values here are given by Eisenstein series. It means maybe I will. So here you can obtain the partition function associated to lambda 1 and lambda 0, and when you divide by identification with the left, you have the values. So maybe I give you the values here. Yeah, if you make the Q expression of both sides, you obtain the relation by all these kind of partition function here, and with the divisor function. This is right side is the left side is the divisor function associated to Legendre samples here. Okay, and you have one and the other one, and for example, it's very curious. The last one you have 5 everywhere, and if you look at modulo 5, this partition function is exactly 0 modulo 5, for example, or all. And this is another point of this is this kind what I want to tell you, this kind of relation can give you Ramanujan congruence for others partition function. Look at only the coefficient. For example, here, if you look at modulo 5, this is go to 0, and this partition function is exactly the divisor function. The sigma divisor here of n. Here. Partition function here, modulo 5, is exactly the divisor, number of divisor of n twisted with the character. So it's very, and this right side, left side can be completely easily. And this one is very complicated, but you have the behavior here. No, maybe now I finished what I want to tell you, but I want to, as I tell you before, what behind, what is the toll of this kind of, where it comes from, all these methods. Just to summarize, now if you want, if you consider again the Eisenstein series associated to character Q. If you want the classical one, take only the trivial character, and you have, if you take the trivial character, you have the Eisenstein series, the classical one here. And what we know in the modular theory, those kind of Eisenstein series are modular forms of white R and associated to congruence group gamma 0p. And the second, and also we can come from one to other one, from V and U, by using the transformation formula, 1 minus P2. This is the transformation is not, this is not in, this kind of transformation is not in gamma 0p, but it controls what we call the cusp. The cusp, if the cusp of the gamma 0, the modular form, the modular curve gamma 0p. So there are connection with this and this. What is the philosophy behind this? It says if you have some formula for this, if you succeed to prove some formula for this, you can obtain immediately formula for this by using this kind of transformation. It's not easier, but you can. And if you have for this some result here, you can obtain for them, and vice versa. So using this kind of result here. So, and yeah, if you have some modular form for white air and gamma 0p, Newman give method how to connect any modular form for white air and associate to gamma 0p to eta function. And I will give you the K of the Newman method. So Newman method give, you can, you check, you take, this is, if you have white air and gamma 0, where you want modular form white air associated to gamma 0p with character. So you choose any S like this, good, and you choose R satisfying this and also this. If you have all these kind of conditions satisfied, you obtain modular form like this. Very difficult, very Newman make maybe 3 or 4 papers to prove all the this proposition, this result. And but he doesn't apply this, but it's very powerful. It's very powerful now. If you understand what is how to use it, what behind this, you can obtain many modular equation. So and 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 we must connect. It's not really sufficient all these conditions. He proved the modularity. He say here he proved, he constructs, if you take white air and level P, you obtain some modular. forms. But the problem is this kind of eta function can be expressed any modular forms in this term, with this. And later, the question is solved by Liguza in his thesis, I think in 1975, really recent, not so maybe 50 years ago. He give condition, we call it now Liguza's condition, how to construct effectively cusp form of gamma 0p. And you must some condition, and it depends to the genus of gamma 0p. So there are, I give you maybe later the reference for this. For example, in our situation, for the Eisenstein series, you consider this trick. The trick is that if you want to obtain some result for this, it's very difficult to consider directly this series. You must multiply by some eta quotient, and you obtain some result very easier like this. If you multiply Eisenstein series by this eta quotient, you obtain modular function. Modular function is more easier, and you have Q series, and you obtain the problem we have, if you multiply Eisenstein series by this quotient, you obtain modular function. Is specific and particular modular forms. I don't see here modular form. The modular function are more simple than modular form, and they have more ingredient to catch it. And this is if we have this another method come later, which we call it Sturm method, and we can exactly effectively finish the theorem. Here, I applied this theorem to those kind of method to L equal to 2, 3, 4, 5, and so on, and we can obtain more result. For example, if you you consider this. This is the final step of the method. If you take this example, for example, you can prove by that lemma and proposition are modular function for gamma 0.5, and the geometry of gamma 0.5 by Liguza tell you that the modular function are Hopf module. It means that all modular forms, all modular function can be as a polynomial in this kind of function, this eta function. And now the problem is this is polynomial, but the problem how to find those kind of coefficient to finish the problem. And that one, it comes from what we call it good basis or Milner basis. And so Milner basis, it give you finally what is the coefficient A1, A2, and I tell you what is in this case what is the Milner, what is the in this situation. You have this. Milner basis. You have some kind of eta function. This one start with K3, the other one start K2 and Q, and you obtain some linear system, triangular linear system, and you obtain immediately your coefficient, and you obtain the formula for this by this, and you finish your and you prove your formula. Now, if you prove, as I tell you before, formula for U6 with this Eisenstein series, you can immediately obtain for view by the transformation. This you can come from U6 to V6 by using one of the fundamental theorem I show you before. So, and you make transformation for formula for eta function, and from this one you obtain this one. So maybe I will stop here, and yeah, you can do it for any others. And thank you for your patience. Maybe I take more times. Sorry. Thank you.
Thank you very much, Professor Bayat, for the interesting presentations. Now we begin the question and answer session. For the online participants, you can type your question in the chat box. For those here in person, please raise your hand.
Professor,
yes,
you have delivered a very wonderful talk. Thank you very much.
Thank you.
Thank you. Yeah.
Thank you. Thank you. If you are interested, you see my slides. You are the reference in my slides. So thank you for your invitation, and maybe see you next time.
Yeah.
Okay. See you.
See you then. Yeah.
In conclusion, this presentation explored the mathematical structure and deep relationships between Eisenstein series and the dedicated eta function. These ideas are not only beautiful in pure mathematics, but they also connect to number theory, special function, and modern application in areas. Thank you very much. Give applause for Professor Bayat.
Ladies and gentlemen, before we entering our next presentation, we will appreciate the keynote speaker by giving him certificate symbolically to Professor Abdelmajid Bayat. Thank you very much to Professor Abdelmajid Bayat for the fantastic presentation. This is your certificate as the keynote speaker.
Now we continue to our next presentations. Our next speaker is Professor Dr. Andes Davik, MSc PhD from University of Jember, Indonesia, as well as President of the Indonesian Mathematical Society. Professor Davik currently serves as the Dean of the Faculty of Mathematics and Natural Science at the University of Jember. He is a senior and highly respected scholar in combinatorics and graph theory, with particular expertise in network topology and mathematics education. Prof. Davik completed his advanced studies abroad, earning his master from the University of Manchester Institute of Science and Technology in the UK, and his PhD in mathematics from the University of Ballarat in Australia. Since his appointment as professor in 2013, he has been at the forefront of mathematical research and innovation, leading the research group on combinatorics, graph theory, and network topology. His work continues to inspire both students and fellow academics in Indonesia and internationally. But Rafiq, the time is yours.
Yeah, thank you, moderator Syahbana. I'm the last one. I'm presenting on behalf of, actually instead of Professor Taekyon Kim, who cannot join in this conference. My title of talk is prototyping. I'm just yeah. My title of talk is prototyping document watermarking with rainbow anti-magic coloring for secure blockchain-based digital certificate. This is funded by RIM Kompetisi BRIN 2025. As a motivation, network security is really forming a graph. So, moderator already said to you that's my research of interest, average in graph theory. And advanced blockchain technology enforce us to have more security in transaction, even only in end-to-end technology, in perbankan misalkan, and also in cryptocurrency that we have already known so far for the young researcher or young student also know about the cryptocurrency, which is blockchain of decentralized finance type. This is now the new issue in the Ministry of Education. They will issue and they will encourage the university to have digital certificate for the graduates. So implementing digital certificate, it's not easy since they need satisfy this kind of properties. The first is trust. Authenticity, of course, should be complex and should be validated and should be real. Each certificate must be probably real, tamper-proof, uniquely issued, and link it to the graduate. And finally, also in this case, we need like QR code, for example, digital signature, watermarking, and blockchain hash. Another one is easy verification for outsider, employers, scholarship, committee. They will use it, this one, even also the company, and also we need a QR code and watermarking as well. And strong ownership for the graduate. That's why we propose the use of the platform call it Phantom, for example, NFT, OpenSea, because the ownership should be belong to authorized person, authorized graduates. Integrity and security of the record, the data cannot be edited by quarterly after issuance. The system should long who issued what, when under the authority. This one also need a watermarking. Also official in legal recognition. That's the property of the sticker. So that's why in our research of study, especially this year, we focus of image watermarking. So what is image watermarking? Watermarking is a technique used to embed hidden information into digital media, such as image, audio, and so on. That's watermarking. So watermarking does not mean like a document watermarking. If you have a Word document, for example, and then you put draft, for example, Word in that, that's not watermarking that we mean. The watermarking is hidden. It is inside in the document file. So there are a lot of watermarkings, classical method, for example, least significant bit, frequency spatial domain technique, and then split spectrum watermarking, quantization, dash and ice watermarking, discrete wavelet, and cosine transform. We will use this one to compare our watermarking technique with our what proposed result. So this is a watermarking normally we use when you have an image, you want to send this image, and then we embed with a key, and then the image become watermark image. And then when you send to other receiver, then the receiver will extract the image and finally you can have the original image. This is the watermarking system. So when you embed watermark into image, and then you need the key. When you want to decrypt the watermark, extracting the watermark, also you need a key. So that's why very complex system here. Then we propose the rainbow anti-magic coloring as the solution for watermarking. So what is a blockchain technology? Blockchain technology is decentralized and distributed ledger system that secure record transaction across a network of computer. It's organized transaction into block, with each block referencing the previous one, forming an immutable chain. Decentralized achieved through consensus mechanism like POP, proof of work, like POS, proof of stake. So I believe the young generation now about decentralized finance, they are normally using proof of works and proof of stake. So this is a blockchain. So compare with the traditional, for example, centralized finance here. If you have, for example, money and then you save money in bank, and then the bank will know about the amount of your money, and bank will do, we can do anything actually, but you store the money within long time, and bank maybe can be operating the money for other special purpose. Of course, you are safe there, even it is like deposit, for example, in other type of the merchandise of a bank offer to have saving money. But nobody can know about your money in your account. But it is considered to be decentralized. Only bank know about your money. But within this distributed network, it is a concept of a blockchain. Everybody will know about your money in your account. For example, in the platform of the Phantom, using MetaMask and everything, there is a Phantom viewer in the internet, then everybody can view your existing of your money. So for example, Bitcoin, Ethereum and everything, this is a decentralized finance established by Satoshi Nakamoto 2008, and also Ethereum Vitalik Buterin from Russia 2013. Until now is still available, even it is fluctuative. For example, yes, even gold also dynamic, the price, yeah. Then the other thing that we can use for watermarking and also for blockchain and distributing the certificate, we call NFT. This is NFT created by Kevin McCoy, that and a collaboration with Anil Dash in May 2014. It was minted on the name coin of blockchain. So we use NFT because NFT is image processing as well, and blockchain certificate making is possible by under the NFT technology. So this is the quantum agent. Yeah, this is the NFT that's very popular, and so far it is very fair in the OpenSea right now. NFT. Yeah. So with using two keys that we call public keys and also private key, make it the blockchain is become very complicated to interfere by unauthorized people, because in the blockchain, if you store the money in the blockchain, it is not written your name, it is written a hash function. So she likes the public key here. If you want to transfer the money, and then you send very long hash key, so it is very hard to introduce. Yeah, okay, so this is a blockchain technology, and then we have this hash function, and then we have store in the ledger. This is a concept of a blockchain. And then come to our concept in the graph theory. we will use this graph theory for watermarking technique in digital certificate, what we call rainbow coloring. In rainbow coloring, we have this definition. Rainbow coloring first introduced by Chartrand, John and McCann, Pisang 2008. What is that? Let G containing vertex and edges be a connected, undirected and simple graph, and then with a vertex set an edge set EG for a coloring C, mapping from H element to a number 1 to up to K, where K element of N. Then this graph is considered to be a rainbow if there exists part in G. Then if no two edges of P are colored the same. There are a book written by Li Zuliang Li and Son, Yufang 2070, about the dynamic survey. It is update dynamic survey on rainbow connection of a graph. This survey, they attempt to organize some researcher work into a following category. There are a lot of things there: rainbow connection, coloring of age version, vertex version, and everything. I'll telling you about the rainbow. This is the rainbow connection concept here. So the rainbow connection concept, if we have institution, another institution, we have 7 institutions here. If you want to send a message, then the message should pass a distinct password, a distinct firewall along this. Then simply we can assign the rainbow. The password is 1, 2, 3, 4, 5, 6. It means there are 6 number of distinct password, because it is considered a rainbow path. But if the computer network form in this structure, this is considered to be bipartite graph, then it will very easy to have a rainbow connection number of this structure is equal to, for example, from here, to traverse from this vertex to this vertex, and then we have a blue color, and then the other we have red colors. So the other one, if we want to go to here to there, and we have red color and we have blue color. So meaning the rainbow connection number is 2. What about if this structure, and then we will assign, well, what is the rainbow connection number? Is it 2? No, we will have more than 2. For example, here, this is 2 vertices. If you want to travel from this vertex to that vertex, of course, at the moment you can have red and blue. But what about from here to here? Yeah, you couldn't afford to have more than 2, because you couldn't go to this one, and then again you should go to that destination vertex. Then we have more than 2 colors, then it is 3 color, then consequently the rainbow connection number of N is 3. For example, here as well, this is a graph, then you have a rainbow connection number as many as 8, because there are 8 different color. From this one, 6, 5, the very and the left hand side and the right hand side color, vertices, and then you have this one. That is the rainbow. There are a lot of type of rainbow study. Also, some colleges from ITB also, Professor Salman with his student also working on rainbow connection numbers, and even there are a lot of rainbow related type of the rainbow connection number. But in our case here, we focus on the application of rainbow connection number into watermarking digital certificates. So this is that I am very happy to have this one, because we already succeeded to write a code in Python, and finally we can run the Python very smoothly, and then we are ready to publish our result. So I'm also writing a book on rainbow connection of graph, yeah, and some others people, Zhu Liangli, Yusef Fang San, and Gary Chartan also have a book. And this is the anti-magic labeling. In our case, we do not only focus on rainbow coloring, we only also focus on rainbow anti-magic coloring, meaning there are a combination between rainbow coloring and anti-magic labeling. So that's why in this case, we introduce you also about anti-magic labeling. But we do not know we do not read this one into a little bit detail because it is also already done by Harfitz and Ringel in 1990. It is a little bit long time ago. And I will give you an illustration about the anti-magic labeling. So if you have a cycle, for example, of order 13 here, how do we assign the label into a vertices such that all the H weight, which is a summation of two adjacent vertices, are distinct. So for example here, we have the summation 7 plus 1 is 8, 1 plus 8 is 9, and everything are distinct. Yeah, but it is anti-magic, not rainbow coloring yet. Yeah, so it is anti-magic. So there are a lot of anti-magic study as well, and then we have a publication in the top journal in Discrete Mathematics 2009 with Merka Meller, Joe Ryan, Professor Martin Bacha, and nowadays we have a lot of publication with some Indian scientists also joined in this conference in this morning, Professor Lokesa and also Professor Venkatachalam. So now the combination of rainbow coloring and anti-magic coloring, now we end up with the new definition, a new notion that we call rainbow anti-magic coloring. Previously, Professor Venkatachalam combined packing coloring and equitable coloring become equitable packing coloring. So this is like graph scientists like this type of idea very much. If we already have solve our problem and then we propose a new problem, and sometimes if it is already in the upper bound, we already found all of them and then we combine the definition. So it is very, very quite normal in our case. So this is a rainbow anti-magic coloring. It is different now. So if it is rainbow coloring itself, we start assigning label from ages. But if it is rainbow anti-magic labeling, we assign label into vertices, and then we consider the H weight, whether it is different or not. And finally, we have rainbow anti-magic coloring. So this is a rainbow anti-magic coloring. Now, we have a lot of publication about our result in this recent years about rainbow anti-magic coloring, either an H version or an Vertex version. So this is our book. We already have also some what books is. It is a series. Now we update this book yearly, Super H anti-magic total labeling, and also we have a rainbow anti-magic coloring itself. So Super H anti-magic graphs. I am also the editor of this book, written by Professor Martin Bacha and Merka Miller. So now we are talking about rainbow anti-magic coloring for image watering. So if we have this rainbow anti-magic coloring study, of course, we propose the first one is a lemma and theorem. And then we prove the lemma and theorem logically until some other people are convinced about this proof. We have lemma 1, we have theorem 1, theorem 2, theorem 3. We already combined. This is the upper bound of the rainbow anti-magic coloring. Rainbow anti-magic upper bound is greater or equal maximum RC of G, RC meaning the rainbow coloring itself. And delta, big delta is a degree of G. Now we have this proof. Okay, for example, we have theorem 3 and theorem 4. I'll give it to you. Not all of them I'll give it the proof, only for theorem 4. So when we start to prove some theorem in our labeling site or coloring site, normally we start to tabulate the vertex set and its set and find out the cardinality. Yeah, in this case, the cardinality of vertex and cardinality of this one is here. Yeah. And then after that, we try to have a upper bound. And then one the magic coloring connection number of amalgamation of this graph is maximum RC. And then we input the number and finally we have this upper bound. Then we prove the upper bound by defining a label function of phi and as follows. We have this function. Yes, a normal way that mathematicians show the proof, normally writing a very long bijection or injection or whatever. So we have this one and so on, and then after bijection, and then we also develop a formula, a sets of each weight of this each weight we splitting into special cases, for example W, Z, X, I, G and everything. And then finally we prove the number of sets of which either the sets attaining the lower bound. So by using a simple arithmetic sequence formula, and then finally we have P R plus 1T. And then we can say that we already attaining upper bound. So lower bound we attain and then upper bound we already attain, exactly the same. Then we can say that the theorem proof. Now we have a table for convincing the people, table containing the rainbow path and then a condition, because the one of the properties of rainbow connection, rainbow anti-magic coloring is the existence of rainbow path and also the rainbow anti-magic connection number attaining the lower bound. So here we can show that this rainbow path is exists every two vertex, every two distinct vertex. If you would travel from each vertex to other vertex. Theorem 5, the same proof. The way how to prove is almost the same. And then we start with the tabulating the vertex set and each set and everything. So we have this also the proof. And finally, the proof also attaining the lower bound. The upper bound is also the same. And finally, we can convince that this proof is logically proven. So we have 6 theorem altogether here, and then we do not know further about this what proof. And then finally, how we implement this concept of rainbow anti-magic coloring into watermarking, digital image watermarking for distributing a certificate, for example. And firstly, we use least significant bit here. So we extract the figures and then finally we get the matrices, and then we partitioning the matrices into a binary code. Here is 1010 is binary code. And then we use the rainbow anti-magic coloring graph, and then we try to tabulate the adjacency. And then we have already the adjacency, and we have the rainbow anti-magic coloring labels. From this label, we create a block, and then divide this block. We embed this into image by blocks. So, of course, doing this one is not able to be done by manual or technical calculation. Then we write down according. So this is the program of image watermarking in Chitra about the RGB, red, green and blue. So we have this one. By this coding, and then finally we can get this one. So this is the original image, and then this is the watermark image. Original image and watermark image. So if we have ijazah, for example, and then when we produce a number of certificate for graduates, we need to watermark first before distributing the certificate, the ijazah to a graduate. So that's why it is very important, because if we do not doing a watermark and finally somebody else can copy. So just like right now, we have a lot of issue, a lot of news about the hijacking the certificate. Yeah, that's you can see in the YouTube or in the social media. That's someone doing something like this. Yeah, by this watermarking, and then finally we can check it. After we watermark the document, we can check it. If you want to apply to a company to apply a job, the company do not need necessarily require your paper certificate, because in Malaysia, in Singapore, also in Australia, if they apply a job, they don't need to send the paper, and you make it legalizer for your certificate, legalizer ijazah. It is not need anymore by digital image watermarking. But of course, the company should access the provider also platform. They can check whether it is originally issued by University of Udayana, for example, issued by the University of Jember. But before that, we can put a watermark inside, we can put QR code inside, we can also have ownership for the authenticity. Yeah, that's mean we need to have the what we call a blockchain. Otherwise, people can have this PDF file, the document, electronic document easily, even they are not authoritas person. So this is the example that I already put in the OpenSea already. I gave a certificate to Indian student already, Dr. Sam, one of the my student under the international postgraduate research program. When he accomplished their joint research with us, a postgraduate research program, and then I give them a certificate. The certificate can be downloaded from OpenSea, but they should purchase using a platform that we call Phantom. And then it is there is a purchasing program. With this Phantom, the authentication more stronger, because in Phantom there is a ownership address that we call public key, which is showing the hash function, hash number. And then we've put this one because my research is prototyping digital watermarking, and then we put this one in our platform. So in here there is a course somewhere here is there is like international postgraduate research program, there is summer course and everything. All those certificates are digitalized. But before that we do watermarking, and then we upload certificate here. Only the authority people can access this one, and the company can access whether this certificate issued by SIGAN EduTech Centers, because this is SIGAN is our my research group in the University of Jember. It is award formally issued by the University of Jember. So this is a platform. So we already finished this prototype, but inside prototype, in the dashboard, there are a lot of coding and there are a lot of watermarking problems. So in terms of the mathematical side, of course, we need to know ablasan study, because when we have a publication, we submit to a top journal or to Q1 journal, we need to publish and study. Not only producing a prototype for patent, for everything, I believe so. This is also very hard. This is what intellectual, property right is also very easy to find out now, but for patent it is very hard. So that's why for proposing the grant, normally we need to have a prototype. But apart from this, we analyze the key length, key management, algorithm strength, randomness, entropy, cryptanalysis, and set everything. This is just for testing whether our result is strong or not, result is effective or not. We compare watermarking using rainbow anti-magic coloring plus LSRB, watermarking using ES plus LSB, watermarking using DAS plus LSB, then we have this kind of thing. Of course, in here we have a very effective and also the R correlation is very, very high. And compare with the histogram of original image, we can show for this case also, then comparison original with watermarking image, but compare with the other, it's not too different. Even we lose the resolution, but it's not too different. So the university still can keep the original one if the student requires. But if the student not requires, the original one can be stored in the university storage. So because they already have file, they already have their authority and ownership there. So it will be done for the future. That the only thing that we just now synchronizing between the university producing the digital image with the company which use the digital certificate for a special purpose. So this is the tempered detection also. It is very very nice result here. Watermark, then we have 0.54% and everything. So I believe this one from me for the future research, especially for a young student. Yeah, you are welcome to join with our research group working on graph theory and application. We also working on machine learning and our deep convolutional neural network. We also produce some application from classification, clustering problem, and doing with the people from mechanical engineering and also from civil engineering, and as well as we are working with the biotechnology people also for bioinformatics and everything. So for this rainbow anti-connection number itself, it is wild problem. So it will not be finished within 10 years study because there are a lot of type of this age of vertex rainbow anti-magic connection number, rainbow of strong total anti-magic coloring, and vertex rainbow of anti-magic coloring. And finally, we have also strong rainbow anti-magic coloring. So this is my publication with other people. Also with Lokesa, we have 2023 on study of rainbow anti-magic connection number of product of friendship of graph. There are a lot of that you can browse my Scopus author profile there, and then you can find also in the other resources like ResearchGate to download the publication. So that's all from me, and then I give it back to moderator to have discussion. Yes, please. Yeah.
Thank you very much, Professor David, for the interesting presentations. Now we begin the question and answer session. For online participants, you can type your question in the chat box. For those here in person, please raise your hand. In conclusion, this presentation shows how rainbow anti-magic coloring from graph theory can be used to build a watermarking system so that tampering can be detected and ownership can be proved. By combining this watermark with cryptographic protections and storing the certified image on blockchain and NFT, the method supports safer digital certificate distribution and transparent proof of authorship in real time. Thank you very much. Give applause for Professor David.
Ladies and gentlemen, before we entering our next agenda, we will appreciate the keynote speaker by giving him certificate to Professor David. The certificate will be delivered by Prof. Komang. To Prof. Komang, please welcome. Thank you very much to Professor David for the insightful presentation. This is your certificate as the keynote speaker.
Mungkin saya berbahasa Indonesia. Nanti besok sore, besok pagi kita ada opening ceremony. Nanti Prof. Komang mohon menambahkan opening ceremony di tempat ruang dekanat ya, Bu Sri ya. Yang tadi itu ruang dekanat ya. Dekatnya kita presensi tadi. Di belakangnya ada remark nanti dari Prof. Lokesa, dari Prof. Komang dan saya. Setelah itu kita akan pergi ke parallel session. Tempatnya di mana Prof. Komang? Di FMIPA. Tapi walking distance ya dari sini ya. Ya kita bisa berangkat bersama-sama nanti. Khususnya yang presentasi offline. Nanti malam tolong sampaikan kepada handai tolan termasuk istri atau putri atau siapa saja yang penyembawa untuk datang ke sini untuk kita ada gala dinner. Terutama yang ada di sini ya. Yang online tidak bisa gala dinner. Yang offline ya. Monggo kita menyediakan banyak menu dan banyak jumlah sehingga saya welcome. Jam berapa itu? Jam 7, bagaimana Prof. Komang? Ya, monggo nanti diulangi lagi oleh Excelsa, karena ini tampaknya mungkin ada yang English spoken, silahkan diulangi lagi. Prof. Komang ada yang bisa disampaikan? Sampun, ya saya kira itu.
And with that, we have reached the end of session. On behalf of everyone, thank you to all our speakers. And I will give back to Master of Ceremony. Thank you from me as moderator for this plenary session. Assalamualaikum warahmatullahi wabarakatuh. Om Swastiastu, salam kebajikan, dan salam sejahtera untuk kita semua.
To all participants, please come to the stage to take the photo session for documentation. Mungkin bisa dibagi menjadi 2 baris. Disilakan untuk menempati tempat yang kosong. Ya, silakan. Oke, baik. Akan saya pandu dalam hitungan 1, 2, 3 gaya formal. Baik, 1, 2, 3 gaya bebas. Dan silakan teriakan Balinya dalam 1, 2, 3. Bali. Oke, terima kasih. Disilakan untuk para hadirin menempati kembali tempat duduk yang disediakan. Okay, ladies and gentlemen, may I have your attention, please? Before we officially close today's conference, I would like to make 3 brief announcements. Mau ngasih pengumuman-pengumuman. Okay, ladies and gentlemen, before we officially close today's conference, I would like to make 3 brief announcements. First, after this session ends, coffee break will be available for all participants. You are warmly invited to enjoy coffee, tea, and light refreshment, which are served just outside this room. And then second, I would like also to remind you about the gala dinner this evening. The gala dinner starts at 7 p.m. in Central Indonesian Time, and it will be held in this building. And third, I would like to share information about the optional tours available for tomorrow. We offering 2 packages. First, Uluwatu tour package. The price is 350,000 rupiah per person with a minimum of 2 persons. This package includes the car, petrol, driver, and entrance tickets. The destination for this tour are Nusa Dua Beach, Pandawa Beach, and Uluwatu. And then second, Tanah Lot package. The price is 380 rupiah per person with a minimum of 2 persons. This package also includes the car, petrol, driver, and entrance tickets. The destination for this tour are Taman Ayun Temple, Alas Kedaton Monkey Forest, and Tanah Lot for the sunset view. If you are interested in joining any of these tours, please contact the committee at the registration desk so we can help you arrange your group. And one more important announcement for tomorrow, all participants are kindly asked to wear the purple conference t-shirt. Once again, tomorrow please wear the purple t-shirt. Okay, ladies and gentlemen, time goes so fast and now we are entering The last agenda that is closing. To online participants, don't forget to fill the list of attendees. The link is available in the Zoom chat column. As we conclude, let us express our gratitude for the smooth running of today's event. May this conference bring benefits to us all. For the last, I do apologize if there were mistakes. Thank you very much for your kind attention. Finally, this is the end of the first day of IndoMS International Conference on Mathematics and Application 2025. Thank you.